See, this time when I started the recording, it did not turn off my camera, nor did it turn off my mic, nor did it turn off my sharing. So that's what students told me last time. Maybe it's because I started the recording, and that's why I turned everything off. And sometimes it does, but sometimes it doesn't. I just have no idea what the rhyme and reason is. So welcome to office hours. I don't have the slide up, but do know that anything you say or chat will be part of the recording. We will share the recording at the end of the office hours with the rest of the class, so be aware of that. Today we'll be going over mostly uh, middle spinning trees and max flow, but I will go over TwoSet like I promised last week. So hopefully that will help the students who asked for it. I do want to open with a few words about exam one. I know that a lot of students got their exam grades back. Hopefully you all have aced it, or if not aced it, at least did well enough to be able to ace this class. For those of you who did not get the grade that you were hoping for or expecting, I do want to give a few words of encouragement. You can bounce back from it if you try it, not to just say like, oh yeah, anybody can bounce back from it, because I personally on my first exam did not do very well on the exam. Funny story was that I had applied to be a TA for the class. I was very enthusiastic about the class when I was a student. I helped a lot of students. I wrote a lot of notes. I even helped answer a lot of questions in the Piazza at the time. And Dr. Brittle and Rocco, who was a head TA at the time, immediately said, yeah, sure, we would love to have you as a TA the following semester. And this all happened before I took the first exam. And then I took my first exam and I did not do well at all. I was below the median grade, and I basically was distraught. And I just, talked to Dr. Brittle and Rocco, and I was like, hey, so I'm probably not going to do well in this class after thinking I would. Would I still have a opportunity to be a TA? And they were very nice about it. They said, a lot of students bounce back, just keep going at your pace, and then maybe work a little harder. So I took that to heart. And after my first exam, I actually thought I was studying a lot. I studied really, really hard. And so going into exam 2, exam 3, I just studied harder. And that's really I know that doesn't sound like a really good advice. I'm a believer that no matter how much effort you put into something, there's always somewhere you can find more effort to be put into it. So if you didn't do well on the first exam, or if you misunderstood the question, or if you figured out what you did wrong in the first exam, just put more effort into it for the second exam. And typically, the second and third exam, students typically score higher. There's various reasons for this. One is that there's a survival bias. All the students who did not do well in the first exam tend to drop the class, and then those students who did well in the first exam are in a position to do well the second and third exam. The other thing is that you now know what the pacing of the exam is. You now know what the exam format is. You now know what the expectations of the exam is. There's various studies out there. I don't know if you guys remember taking SATs, but there's a lot of professional SAT services that'll be like, yeah, we guarantee you a 200 increase in your SAT grade if you come to us. Part of that is because they know that a student taking a test the second time around, knowing the format, knowing what that test looks like, will just naturally do better, even if they don't do any additional study. And so that can carry forward into exam 2 and exam 3. You now know the pacing of the exam. If you think oh man, if I just had 10 extra minutes, 20 extra minutes, an hour more, and I would have done well on the exam, or oh yeah, now that I had seen the exam, I wish I just studied this one part a little better, or I would have taken that advice from this TA a little bit more seriously. You can carry that into the second and third exam without actually being better at any of the algorithm topics, right? That experience can only help. So I do think that most students, if they just, if they didn't do well in the first exam, if they just kind of use that as a stepping stone, a stepping block towards their second and third exam, they just naturally will do better. And your first exam, the way we have a weighting in this exam now is that the exam that you do the worst on matters the least towards your overall grade. So if you do really well in the second exam or the third exam, you can still get an A. So I ended up the semester with an A, even with a really poor first exam. And some students will say, well, you had a final exam replacement at the time. I didn't even take the final exam. So I got a 90 something score without a final replacement. And that was just, me deciding that I wanted to learn more about algorithms. So hopefully that was a little bit inspiring. Hopefully you can use that to sort of motivate yourself going into exam 2 and exam 3. Okay. The other thing I want to mention is that I've seen a lot of discussion on I think it was problem 1, the divide and conquer problem, especially between the comparison of if n is greater than m, what does that mean? What does runtime mean? Are the two runtimes equal? So first of all, try not to be combative with your TAs. Your TAs want to teach you and they want to work with you to learn what that means. But if students come at it like, in a very aggressive tone, the worst thing that can happen is a TA might just not feel up to the moment to respond to you. You want a TA to respond to you because that's how you can properly learn the material. Not that that's the only way to learn the material, but if you're confused about material and you want someone to work with you and help you understand it, asking a TA for guidance or asking a TA to answer you is a really good step, right? And if your tone, even if you're trying to learn, like if your tone is somewhat off-putting, maybe one of the TAs will answer you. The TAs aren't required to answer you, so some of them might not. So I think that's sort of self-defeating. And the other thing is that if you didn't get that problem with an optimal solution, your mindset, and I know this is going to be hard to nail down, but it's not whether the TAs agree that it's optimal or not, or whether Dr. Brittle thinks it's optimal or not. It's not an opinion, really. If you look it up, like if you go, ChatGPT, Gemini, whatever you want AI to help you with it, if you ask that question, it is very clear that there is a distinction between the two runtimes. It is a fact. So you might be able to, not to say you'll get any like movement with it, but you potentially will be like, I don't think the penalty is fair. That is a valid statement, given how subjective rubrics are in general. And that is at least a valid conversation to be had. There's a starting point of that conversation. Arguing that one runtime is not optimal versus other runtime, that is a non-starter because it's an established fact. You're not arguing against the class. You're not arguing against your grader. You're not arguing against Dr. Bretto. You're arguing against like established, big old notation runtime understanding. Like it's not this class that's forcing it. It's general understanding. And I'll go over some of that on the graphs on why, like, if one piece of your runtime is worst case less than or equal to another, that still doesn't mean that the two runtimes are the same. It's much more easier to see in graphs than I think in Divide and Conquer. So I think it would be a good time to sort of cover that. So yeah, that's just how I want to get those. I want to calm the students down a little bit. Hopefully, we can have good relationships going forward. All right, I'm going to cover two-set. All right. So the way two-set works is that you have to understand what a CNF is. You have to understand. So hopefully that's covered in lectures. If not, look it up online. It should be pretty universal, self-explanatory. So a CNF, one single clause in the CNF looks something like this. So you have one literal or another literal that would satisfy this clause, right? A two-set specifically means that all the clauses in the CNF are one or two literals. Max two literals. So a three-set would be a max of three literals. A four-set would be a max of four literals. And it turns out that two-set, specifically two-set, is solvable in polynomial time. We'll cover what that means going into the next topic, but it is something we can solve in linear time. Oh, n plus n. Okay. And you can read this So this is saying that either not A is true or not B is true. They can both be true, and that will satisfy the clause. One of them being true will satisfy the clause, but they can't both be false. And because of this, there's only two literals within a clause, we can reason out all the implications of this in a timely fashion. So we know that if not A has to be true or not B has to be true, then if A is true, then not A must be false, right? There's a relationship between the two literals that represent the variable. So if A is true, not A is false. And if not A is false, then not B must be true to satisfy this clause. Therefore, the very idea that A is true implies not B is true. Okay, that's the logic behind how this clause works. Okay, and on the other hand, if B is true, then not B is false, right? That's just the relationship between two. So not A then also must be true to satisfy this, right? Because if this right here is false, hopefully, can you see my mouse? Let me turn on my pen. If this is false, one of these has to be true. So this one has to be true in order to satisfy this clause. Okay. So then B being true implies not A is true. Okay. These are called implications, and they can be represented as directed edges. So if I want to represent that if A is true, then not B is true, I can make a edge going from A being true must be followed by not B being true. Okay, these are implications, and implications can be graphed. It's actually a good way to represent a lot of logic-based problems. Now, if there's a path from one point to another, that implication carries forward. So this right here is like the symbol for a path. If there's a path between A and not A, I can't set A to true, because if I set A to true, following the implications, I imply that not A is true. And because they both can't be true, A cannot be true in this case. Okay. However, A can be false. A being false is allowed because it doesn't have any implications down this path. So if A is false, I can still set not A to true. Okay. And vice versa. It also means the same. So if not A has a path to A, we also can both be true, because not A being true would imply that A is true. And because they're opposites of the variable, they cannot both be set to true, right? So not A can be false, because if this is false, there's no implications that carry forward. It doesn't force A to be true or false. Okay, other than the fact that if not A is false, then A has to be true because of the relationship. But the implication here is doesn't force A to be anything. Okay. So given these two statements, what happens if there's a cycle? If there's a cycle between A and not A, so like A is able to find a path to not A, and then not A is able to find a path to A, then you have a contradiction, right? Because at least one of them has to be set to true, or exactly one of them has to be set to true. And following that path of implications, if one of them is set to true, they both end up being set to true, and they can't do that. That's bad, right? So that's not allowed. So you want to avoid cycles between the opposites of a variable. Okay. So for all V in our vertices, once we represent a and I'll show you how this is represented in graph form. Once we represent our 2-sat CNF into a graph, for every single vertex, right, or every actually this shouldn't be V and V. This is for every literal, every variable. Yeah, let's do that. Every variable, let's say X. I think X is easier. X and not X must be in different SCCs to avoid a cycle, right? Because if they're in the same SCC, there's a cycle. That's what SCCs are for, and we understand that, right? So with that in mind, once we have correctly formed that graph, what 2-sat does is says, okay, well, we have a source SCC. If we set every variable in that SCC to false, it has no implications to anything afterwards. But there's going to be a complement, right? There should be a complement to that source of all the same variables as a sink. Now we can set everything in that sink to be true, and that doesn't affect any of the previous SECs coming into that sink, right? Because like I said, not A here can be true, and it doesn't impact what A is. And if A is false, that doesn't impact what not A is. So we need to set that up using SECs, and that's what we do. So this is why it works, and then this is how we set it up using the SEC algorithm to solve the two-set. You don't really have to think too much about this because this is a black box to you, but understanding the concepts is important. Okay. Question, Mahmoud?
Hi, can you hear me?
Uh-huh.
So I asked Dr. Brito this question, I think, last time, and he was like, I can't think of anything, but maybe you might have something. When would we use something like this? Like, I'm trying to figure out like a practical application for this algorithm, and I can't think of anything other than just solving logic problems.
Yeah. I mean, so one thing, I think one way to look at it is that even if all this thing does is solve two-set can be a lot of problems can be reduced to two-set. So satisfiability problems are the very like foundation of almost all logic questions. When you get into the NP complete topic, which is coming up after exam 2, you will learn that any problem in the NP space can be reduced to a SAT problem. Which means if you can solve a SAT problem in like all general SAT problems in a efficient way, you can solve any NP complete problem in an efficient way. And that opens up into like massive number of questions. They're all related. It might not be like obvious, but like chess is related. Um, gene voting is related. Um, let's see. There's so many applications that once you can reduce it to a SAT problem and you can solve that SAT problem, that you just solve like a huge variety of problems. Um, I don't know if we have a practice problem this semester that uses two SAT. Um, but if you ever heard of the graph coloring problem, so a graph coloring problem can also be reduced to a two set or a three set or however many colors you have because of the way that they're related. So that's one of them. And coloring problems are, pretty good at about like, there's a lot of like economics, a lot of geopolitical like type problems that can be solved using the graph coloring problem. Does that help? Yes? No?
Kind of. I think I'd have to see like a problem worked out, but I don't want to take up any more time, so thank you.
We will absolutely see problems reduced to SAT problems in the next topic. And then if you keep that in mind when you see those problems being reduced, and you go, oh yeah, and if I knew that the resulting CNF was a two SAT, then I could just throw it at this algorithm and I could get an answer.
But
Okay.
so I think one of the other questions I had is that when you're creating your graph of implications, so for example, A implies not B
Mm-hmm.
and B implies not A, the moment you create your graph and run SCC, and if there's an X and not X in it, it's not solvable. But if they're in two
Correct.
separate components, it is solvable, at which point you can output the result, which would be whatever the following graph outputs.
Yes. Correct.
Okay. And that's mainly the whole purpose behind TwoSat, roughly.
Yes.
Okay, thank you.
Yep. All right. So we're gonna take this example. This is the two set. So this is actually the same as the one in the lectures. I just don't like the whole x1, x2, x3. I just prefer them to be separate letters so that they're easier for me to see. So, but this matches up exactly with the ones in the lecture. So I have A, not A or not B, and B or C and not C or not A. Okay. And the way that these implications work is that you don't actually work directly with the variable that you're trying to build an implication with. You build it using the opposite of it. Okay. So if I have not A or not B here, what I'm really saying is that if A is true, then not A is false. And if not A is false, then not B must be true. Okay. So that gives me this implication right here. And then the other one, so each of these clauses will have exactly 2 implications because you're working with 2 variables. So if B is true, then not B is false. And if not B is false, then not A is true. So this is the other implication out of that one clause. Then the second clause is not B implies C, because if not B is true, then B is false. And if B is false, then C must be true. So this is not B to C, and then not C to B, which is the other side of this. Okay. And then finally, not C and not A is the 2 implications are if C, then not A. So C, then not A. Okay. And then if A, then not C. Okay. So those are all your edges that represent the 6 implications because of the 3 clauses, and each of them has 2. Okay. I'm going to get rid of that real quick. And these are my nicer drawn pre-made arrows. Okay. Now let's run what the 2-set algorithm will say. Okay, so we know that A is a source, right? Because there's no incoming edges, and we know not A is a sink because there's no incoming edges. This is only source and this is only sink. So if we set this to false and we set this to true, okay, we can get rid of these, right? So this goes away. This goes away. Because we're going to rip out the source in the sink, right? That's how we solve for this. So this goes away and this goes away. Now, we see now that not B is a source and B is a sink, right? The other way you can look at it, because of the way thing it is, so not C is also a source and C is also a sink. You can pick either one. Remember how we saw that topological sorting? If there's no predefined way of like choosing which node over which, they can have multiple topological sorting. This is the same way. We may not encounter B as the next source and the next sink. We may encounter C instead, and it actually can change the way that you make assignments, because CNFs can have multiple assignments. So just like there's multiple topological sortings of this, there can be multiple assignments, and I'll show that in a second. So, but we're just going to do B for now. So not B is a source. This is our first source after we eliminate A and not A. So now we set this to false. Okay, which means that this is the sink. We set this to true, right? And then similarly, not C is now disconnected. You can set it to anything. So when these two are completely disconnected, both of them are sources and both of them sync. So you can actually set this to whatever. This can be true or false. Let's just do true for now, and this can be false. Okay. So set it to the opposite. So does that work? So if I set A and not A are opposites, B and not B are opposites, C and not C are opposites, and if I had this as not A being true, this is satisfied. If this had B as being true, this is satisfied. And if this had not C as being true, this is also satisfied, right? So that all works. And just like I said, you could have switched this. Like this could have gone the other way. We could have had C as being async. Oh, I said this is false. Yeah, so it turns out these two can be flipped and these two can be flipped. They can't both be flipped at the same time because then you end up not having it. So in different order, we could have had this as false and this as true, and then this as true and this as false. And that should have worked too. The important thing is that these two have to be set because they're the very first source and very first sink. So this cannot be set to anything else, right? But if I had, say, on this one, I had B not B as true, so this would be both true, right? And that's fine. But here, C is true, so C is what covers this, not B, not this anymore, it's the C. And this one has not C being false, which doesn't cover this, but not A is still true, so this would cover it. Okay, so that still works. And that is how a two-set gets solved by using this, source sink pairing and eliminating them and setting them and going forward. But the first thing to realize is that all of your literals, opposite literals, has to be in separate SCCs for this to even work. And that is the first thing to determine whether this CNF is even satisfiable. And I showed that by saying that if you have a path, it creates the implications. If you have a cycle, you have a contradiction. But if you don't have a cycle, there's no contradiction. You can set things up so that it can be set correctly. All right, any questions about two-set? Nika?
So for that first part, just to confirm, so you just flip the what the literal is. So like if you have not A, not B, you would use AB and you continue that, and then you set the value of the opposite one to true, and then that's how you create your edges?
So one, yes, that is true. If you want a formulaic way of doing it, I think that's true. But I think it's actually better to actually understand the logic behind it, right? When you look at it, not A or not B, right? If I say not A is true, that doesn't tell me anything about not B, right? Not B can also be true. It could also be false. Because not A satisfies that clause, saying not A is true doesn't do anything for me. On the other hand, if I say not A is false, I know not B has to be true for that clause to be satisfied. That is a much stronger statement to make. And what's another way of saying not A is false is to say A is true. Therefore, the logic comes from that, saying that if not A is false, I need not B to be true. Therefore, if A is true, not B is also true. That's the implication you're building.
Okay, that makes sense. And then at the end, once you start, eliminating things in your graph, what's the conclusion? Because that's the part I didn't really understand. Like, if this happens, then it's not satisfiable, and that part.
Right here or right here?
No, on the right, on the graph.
Okay, so what I did here was I basically said, okay, now that I built my graph of implications, because I took these statements and I just built edges among them, and I got these edges based on my reasoning of this clause, I'm just saying the way the two-set algorithm works, this is running through the two-set algorithm. What it does is it looks at it, it finds the first source or a source, and it finds the opposite as a sink. Now, in a much more complicated CNF, there could be multiple literals in these SCCs. This just turns out that each of these are single SCCs, but they could turn out that once you run the SCC algorithm, it might group some literals together. But what it'll always do is group one set of literals together and group the opposite of those literals together. That's just what ends up happening because of the SCC algorithm. And then the rule is, well, I take the source, the first source I can find, or a source, and I set that source to false. Because setting this to false means I can do whatever I want with these next two nodes, because no implication follows from A. Once A is set to false, these implications don't matter anymore. Likewise, by setting this to true, anything can happen for B and C. B can be true or false. That's fine, because if B is false, it doesn't necessitate that not A is false. However, if B is true, that forces not A to be true because of the way the implications are built. But if I set this to true, everything before this, all the pathing leading up to this not A can be something different, and I don't have to know. But I know for sure that this has to be false and this has to be true, and I can start with that. Okay. Once I start with that, I can just rip this out. I no longer care about this. And when I rip those out, the graph condenses to something else. It becomes a slightly different graph. We get rid of all these implications because we've established the assignment for those, and we're good. Now I look at my next source and next sink. Now I can do not B and B, because this is a source and this is a sink, and you have to work on the opposites. You have, like, I can't just do not B and C, because not B and C, even though there's an implication here, they're not related to each other as opposites of a variable. I need to find the opposite, so not B and B. And so now again, I go, okay, well, this I will set to true, and this I will set to false based on what I was talking about earlier. And then once that's done, I can say, okay, I've safely assigned a variable for this. I've safely assigned a variable for this. And I'm left with the two C nodes, and I can do whatever I want with them, because they're unrelated. There's no implication between them. Like C doesn't imply not C doesn't imply C. The only thing you have to know is that they're opposite. So I can just set this to true. I just picked one. It doesn't really matter. And I set this to false. And then that is how all your assignments get created.
So I think I get what you're saying for the source one, but like when you set not A to true, how come we don't have to now put what's upstream of that also set to true? Like how come those implications don't matter for like B and
because
C?
the way implications are, it's a logic statement. If A, then B, right?
Okay.
And if you don't know that, if you don't understand that, there will be a post on implications, logics, and stuff like that. But I do strongly suggest looking it up and learning about them. I actually had to teach this to my my son when he became a freshman in high school. I like did not remember where I learned this. I just kind of like it was in the back of my mind. Apparently, you learn it in high school, so you learn like logic implications in high school. So the whole like inverse and contrapositive and all that stuff. But anyways, if A then B means that if A is set to true, B has to be set to true. But there's nothing that says what A is regardless of what we do to B. There's no implication in the other direction. So B can be set to false, and B can be set to true, and A can still be true or false. But the moment I set A to true, B has to be true because of the implication.
Yeah, that makes sense. Thank you.
Okay, no problem. Michelle?
Hey, Joves, can you hear me?
Yep.
Oh, yeah. So I had a quick question here. So regarding the implications, right? How come we don't have anything between the literal and its negations? Like, wouldn't we have something between A naught and A, B naught and B?
Because the way implications work, it's if this, then that. And there's no such relationship between two literals like that. If A, then not A doesn't make sense. If not A, then A doesn't make sense. You're only graphing implications. The other part of those relationships where the two have to be opposite from each other, you're just keeping it in mind as you're doing this. But there's no way to graph that implication because it's not an implication. Right? Like I'm gonna get rid of this. What would that look like? What would the edge look like from A to not A? If I do this, this is saying if A is true, then not A is true. And that's not what I want, right? But if I go the other way, it also says if not A is true, then A is true. And I also don't want that, right? So that's on this graph, the way this graph is set up, an edge between them it doesn't make sense. But as you're doing this, you should know that A and not A has to be opposites. Does that make sense?
Yeah, that makes sense. Yeah. I was just thinking, I guess how we know this, right? Since we solved the problems that A and A naught are opposite, but I guess were we supposed to show that graphically as well? Like, hey,
there's
no.
Yeah, you're not showing that because there's other relationships, right? That we're not showing. Like not A and not B is in the same class together, right? But they don't have an edge between each other. You're graphing specifically the relationship of implication. Anything else might exist and it might prove useful, but it's not within this graph.
Got it.
Matthew?
Okay.
Yeah, I think you're basically answering that right now, but I want to confirm if a vertex or a literal is not explicitly noted in the CNF, then it does not become a vertex. So like if not A is not listed in the CNF, it doesn't ever become a vertex in a graph. Is that correct?
No, that's not true because you know the relationship with it. You see what some of these are actually missing. A is not actually in the CNF at all, right?
Oh, got it. Okay.
Okay. But you know the relationship between it. You use it as part of your implications relationship.
Okay. Cool.
All right. Okay. think I answered all the questions. So we are going to move to the next topic. This is part 2. We are now doing minimal spanning trees. This is one of my favorite topics on graphs. I feel that, to me, MSTs are the most interesting because they're so heavily related, and the logic behind it is can be confusing until you just start to see it. You start to see the relationships between the weights of the different your different edges, and there's just this feeling of like, aha, I get it now. Hopefully, hopefully before the exam. But yeah, I like MSTs a lot as a general topic in graphs. Okay. Oh wait, hold on. Maybe I lied. Oh, that's right. I moved the BFS Dijkstra stuff forward to week 1 because we had a schedule change. Okay, so minimum spanning trees. Okay, trees have have unique properties. Okay, read up on those properties. They're in your book 5.1.1. The first property is that removing a cycle edge cannot disconnect the graph. First of all, this is all within the context of a undirected graph, right? So don't think about direction on edges. Only think about undirected graphs. When you remove a cycle, you cannot disconnect the graph because by definition, a cycle means that there's 2 paths between 2 vertices. So therefore, if you disconnect that cycle, there must still exist a single path between those 2 vertices, and therefore you cannot disconnect the graph by removing the cycle. Okay, removing an edge from a cycle. Okay. Property 2, a tree on n nodes has exactly n minus 1 edges. It is the minimal number of edges to keep all vertices connected, and so it's exactly n minus 1 edges. Okay, and then that's the definition of tree. And then property 3 is that any connected undirected graph with n equals n minus 1 edges, right, is a tree. Okay, this is the converse of the second property, right? So if A then B, we are conversing and we're saying, okay, well, if A then B, we are also establishing if B then A. Okay, now the converse on a statement does not necessarily have to be true. It has to be in this, a separate establishment of that fact. Okay, just because we say that a tree on n nodes has n minus 1 edges does not automatically mean that a graph with n minus 1 edges is a tree. It is the converse of it has to be separately proven. And I think it's talked about in your book. I'm not going to go through it. Very math heavy. I'll have you guys read about that. Okay. Property 4 says, where's my colon? Okay. Property 4 says an undirect graph is a tree if and only if there is a unique path between any pair of nodes. Okay. So this is a if and only if statement, which means that both directions have been proven by someone much smarter than me. So both if A then B, if A then B, and then we also prove if B then A. Okay. Okay. So if there's more than one path between any pair of nodes, then there's a cycle, right? That is a definition of what a cycle is, right? So because of that, this cannot if there's a unique path between any pair of nodes, then there is no cycle, right? So that is one part of being a tree. And then if there's no path between any pair of nodes, then it is not connected, right? So if it's missing a path between one vertex and another, it's missing a way for them to get to each other. Therefore, the 2 vertices are disconnected from each other, and trees cannot be disconnected. They are a connected graph, and therefore these 2 rules both have to apply to all trees. Okay. Any questions about this slide? Mahmoud?
Yeah, sorry. I think the way property 1 is worded, it's confusing me because, like, we know that there are no cycles. Property 4 says if there's more than one path between a pair of nodes, then there's a cycle, and therefore property 4 does not does not work. So then why is property 1 saying removing a cycle edge cannot disconnect a graph? Why? I feel like there's a weird disconnect in my brain there.
Let me see what type of book puts it. Maybe I put it in a confusing. What happened to property 1? Okay, so I think the way the book puts it might be a little bit more here. It's saying here are 4 properties that you should know. Properties 2, 3, and 4 are around the idea of what a tree, whereas property 1 is more just like a fact. Removing an edge, a cycle edge cannot disconnect the graph. So maybe I'll rewrite this slide a little bit. The first property is not really about trees. It's a statement of fact that leads you to a better understanding of what makes a tree a tree. Does that make sense?
So what do you mean by cycle edge? I don't fully understand the definition of cycle edge then, I guess is maybe where I'm confused.
Yeah, so a cycle edge is like, if you right, so this is a cycle edge, this is a cycle edge, this is a cycle edge. It's just an edge that participates in the cycle. And that means that if an edge participates in the cycle and you independently remove that edge, one of those edges, you will not disconnect your graph.
This is for graphs in general, not related to trees specifically?
Yes. This is for graphs in general, but cycles are very important when in the context of trees. I mean, they're very important in general, but they're especially important in the context of trees because trees have no cycles.
Sorry, I think I'm still a little confused, but I don't want to take any more time, so I think I'll just post my question and end, and maybe someone might want to ask the question, but I don't want to take any more time.
So everything here are associated with what a tree is. Okay. This first property is useful as we talk about trees, but it is not specific to trees. Does that make sense?
The first property is not specific to trees, but it's important for the later properties, is what you're saying.
It's important in the context of how we build trees. Like, or if you want to take another way to look at it, instead of like trying to categorize all these 4 properties, just know these are 4 facts you should know, period. Don't worry about how they're super related. These 4 facts you should know going into exam 2.
Understood. Okay, so property 1, just the property that we need to know in general. 2, 3, 4, specifically related to trees, but because property 4 says there's no cycles, property 1 is sort of related to it.
Yep. There's just 4 facts of graphs that you should know. Okay?
Understood.
Okay. Cut property, super important property that you need to memorize and fully understand. Okay. Suppose edges X are part of a minimum spanning tree. Let's say you're building a minimum spanning tree and you're partially through it. Okay. And you start off with X number of edges that are part of the spanning tree you're building. If you pick any subset of nodes S for which X does not cross between S and VS, and I'll have a diagram for this, and that E be the latest edge across this partition, then X union that edge is part of some MST. What it means is that I'm building some MST. Let's say I hand you a partial MST and I say, I guarantee you these 5 edges together are part of a MST. How do you build the next part to that MST? What you can say is, well, let me look at my cut, which is arbitrarily dividing up all the vertices that are part of X and all the vertices that are not part of X. And if I take the lightest edge going from X to the vertices not part of X, what that lightest edge can be used to continue building my MST. It's a greedy approach. I don't have to know what the next edge after that I'm choosing is, or future edges. MST algorithms are greedy algorithms. I can take my local current knowledge and know what my next best move is, which is all I have is X. I know everything that's not part of it. I just pick the lightest edge across it. As long as it's not going to create, a cycle, I'm okay with taking that edge and moving on. Okay. So this illustration is, suppose you have some X of edges, and you have this S. Okay. You sectioned this off into S, and remember, this doesn't mean that your graph has to be drawn in such a way that these are set up this way and this is set up this way. They can actually be like you might have to do some over under of your circle to cut them apart. But the point is, arbitrary vertices that you've decided this is part of my MST. The rest is not part of my MST I'm currently building. If I find the lightest edge between all these vertices and all these vertices, I can take that edge and add it to my MST, and now that is my next edge in the MST. Okay. So this is how the cut property looks when you run through Kruskal's algorithm. Kruskal's algorithm will sort the edges and start taking the lightest edge, and then just keep adding the lightest edge to it in order to build the MST. Okay. So here is what our graph looks like. Here is what we're going to start building on MST. So my candidates for the very first lightest edge is either this one, this one, this one, or this one. Okay. So just going to pick one arbitrarily, A and C. Okay. Done. This one is checked off. We're going to take that edge. The next one we're going to pick is just, we're going to act as if this is our X. Okay. And so the way the way S and non-S works is that you can just pick one. Okay. You can just say, okay, well, if this is my starting S, my start to my MST, I can just pick a lightest edge from this across this cut. You can make this cut anywhere you want. So across this cut, what is my lightest edge? Well, I have two choices, AC and AB. I'm going to pick this one. Okay. So once I've done that, I'm going to say, okay, these are now my S, and everything that's not in S across here, what is my my next lightest edge? Okay. That is how you can look at Kruskal's, but it also turns out that you don't actually have to do this cutting. You can just start picking lightest edges, and it works itself out, because any lightest edge across a cut, and the cut is completely arbitrary where you want to do it, is considered part of some MST. So this one right here is actually the lightest edge across this cut. Okay, so if I decide to cut my vertices randomly down the middle, 3 here, 3 here, this edge that goes across it can be part of it, my MST. Okay, let's see what the next edge I pick is. This one. Okay, so this edge right here is the lightest edge. I can say that's either the lightest edge across this cut right here. Okay, or I can say that's the lightest cut, one of the lightest edges across this cut right here. Or I can say that's the lightest edge across this cut right here. Any lightest edge across a cut is a candidate across as part of MST, and you can make those cuts anywhere as long as you section off your vertices into 2 groups. Okay. So we're going to pick this one, and then I think we have done. So I think the next one is going to be this one. Yep. And so this would be the lightest cut, the lightest edge across this cut. You can look at it that way. You can also look at it this way if you want to. Yeah. So that is your lightest edge across that cut. And then finally, the next edge we want to consider is one of the 2s, because we have run out of 1s. No, we're not going to consider 2s. The reason we don't consider those 2s is that this would create a cycle. We don't want that. And this also would create a cycle. We don't want that. So these are no good. So now I want to find an edge that crosses this cut to finalize my MST. Which one do I pick? I can either pick this one, or this one. I have 3 edges across this cut. And it turns out it can be any of the lightest edge. It doesn't have to be one specific one. This one is a valid edge. This one is also a valid edge. And that's because the statement of the cut property is that the lightest edge, whether it's unique or not, across a cut is part of some MST. Some MST implies that there can be possibly more than one MST, and it also implies that they're equally valid. So I could pick this edge, or I can pick this edge, and those are 2 different MSTs, and both MSTs are valid MSTs. Okay, so a graph G can have multiple MSTs. That's something you should know. All right, Mahmoud?
So quick question. We went through and selected A, C, A, B, A, D, and E, F because those are all weight 1s. Makes perfect sense to me. No cycles. And then you drew the blue boxes, and from here, we couldn't select any of the 2 edges because they're still in that blue box. So we're looking for ones that are between V and for S, which is the subset, and V minus S, and the 2s are not in that subset effectively, that V minus S component. So we're only looking at the 3, 3, and 4. Is my understanding correct?
Yeah. So
Okay.
the cut property is applied in different ways between Kruskals and Prims. Prims matches the cut property more closely. Kruskals is basically saying, well, I know that if I separate V and V minus S, that I can just take the lightest edge across it. I'm just going to take the lightest edges one at a time after they've been sorted. And the reason that works is because as long as I'm not creating a cycle, each of those edges must be the lightest edge across some cut. Because cuts are basically, wherever you draw a line. And because wherever you draw a line counts as a cut, that edge has to cross a cut. And as long as it's a lightest edge across a cut, it is a valid MST edge. And therefore, I can just choose it without having to care about what's going to be connected later. So Kruskals is interesting because you get a scattering of the edges. It doesn't build from one single. It doesn't start building from here and go, oh, I can only attach things here. That's what Prims does. But Kruskal just says, I'm just going to start picking all my lightest edges. And because those lightest edges are across a cut, they are valid MST edges. And then as I build these random edges from all over the place, not random, but your lightest edge, I will eventually get to a MST.
Okay. And there was a question in the chat, and I think we were talking about it. This works with negative edges as well. There's no reason why it shouldn't. Okay, thank you.
Yep. And this is an important idea, is that because Kruskals and Prims and MST algorithms are greedy algorithms, they work with negative edges. Remember how I told you, I think a couple of weeks ago, that Dijkstra's does not work because it has to know where those negative edges are. But Prims and Kruskals doesn't care. It doesn't, because each edge is only caring about that single cut. And because of that, it doesn't have to know where all the other cuts are when it makes the decision on that single cut. Matthew?
Yeah, did the reason you did not choose 2, did that have anything to do with the cut property, or that was only because of it forming a cycle?
So you can see, 1, it forms a cycle while I run Kruskals, so I don't pick that. 2, those 2 edges are not the lightest edges across any single cut. No matter how I cut this graph, you cannot choose that as the lightest edge, right? So if I choose, let's see what 2 is attached to, right? If I choose to cut it this way, my lightest edges are here and here, right? So that can't work, right? If I choose to isolate C from the rest of my graph, this is my lightest edge, not this, right? So that can't work. If I choose to cut D away from the rest of the graph, this is my lightest edge, not this, right? So no matter how you cut your graph, those edges with the number 2 cannot be your lightest edge, right? If I cut right through here, I have a bunch of 1s I can choose from first, right? Now, why does the 3s get chosen? Because across this cut, this 3 and this 3 are the lightest edges. And that's why even though they're greater than my 2 edges, those are valid MST edges. Okay? So as long as they're the lightest edge across some cut, they are allowed to be an MST. If they are never the lightest edge across any cuts, they cannot be part of the MST. And so these 2s will never be part of an MST. And you can,
Right.
take a screenshot of this and try drawing your cuts and see if you can find contradiction. Hopefully, I got this graph correct, and you won't. But that's why they're never chosen. Now, Kruskal's just in its algorithm when it makes these decisions, doesn't choose them because they will form a cycle. But that happens because the cut property exists.
Cool.
Okay.
Thanks.
Sun Kai?
Hi, can you hear me?
Yes.
Awesome. So there's some discussion in the chat around the order of picking edges. So
Yep.
the first step you pick AC, and the next you pick EF instead of AB.
Yep.
So some folks think this is arbitrary. So is there any like this deterministic order, like lexicographic order to pick the edges or cuts?
Yep. Yep, that's a good question. It doesn't matter. So as long as you follow the rules of Kruskal's, when given the opportunity to pick from multiple edges, it doesn't matter. You can just pick one. It'll work itself up. You may not get the exact same MST edges each time, but at the end of running Kruskal's, all those edges that you pick will be a valid MST. Yep. And we can try it blind. Which one do you guys want to pick first? That's fine. Do you want I don't remember which one to pick. Let's start with this one. This one looks fun. So BD, and then the next edge, we can do AC. Then the next one, EF. The next one, AB. Doesn't really matter. And then the next one is to find a edge that, well, you would have to consider each edge in sorted order. So I would consider this 2. That's not okay because it'll create a cycle. I didn't consider this 2. That's not okay because it'll create a cycle. And then I could either decide on this 3 or this 3. Let's just pick this one. So that's a valid MST. That's fine. And then once all my vertices are connected, my algorithm ends. So I wouldn't even consider 4 because my algorithm's already done. Okay. Any other questions? And I apologize if I missed like a whole lot of it's really hard to try to go through this and keep up with chat. Sometimes I have a helper. I have no helpers today, unfortunately, so it's just me. So I'll try the best I can. But if I don't get to your question, feel free to post it on the ed forums, and either I or another TA will get to it, hopefully. Okay. Mahmoud?
I'm going to try and act as your helper here real quickly.
Thank
there
you.
was a question about how is the cycle detected? Like, how do we determine if, for example, you said that BC would create a cycle? How do we determine that? I think that's one of the questions in the chat. And then another one was, is there an easy way to determine how many variations of an MST exists within a given graph?
Okay. So the first question is you should go read the algorithm book. There is a union find data structure. It's less of an algorithm, more of a data structure that shows how it finds out things as cycles. Basically, it keeps track of what the parent, some candidate as the parent for one set for in another, and if it checks that the 2 have the same parent, it means that they are together, they've been grouped together, and therefore that creates a cycle. So it only takes edges that are attaching nodes from 2 different sets. Union find is not a great. It's one name, but the one I prefer is disjoint sets. It's the exact same data structure. And a student has said that it's an interview question. It is an excellent interview question. my interview question when I used to interview people, I still interview people, but I used to use a disjoint set question because I love that data structure so much. So it is a very good data structure to understand. It's very useful in real life situations, but specifically for calls, that's the data structure it uses to back it. If you look at your homework, the coding problems this week, I believe you will see a implementation of cross calls, and that'll also show the union find data structure in there. Okay, and then I apologize. Second question. What was the second question?
Is there a way to easily determine how many variations of an MST exist within a graph?
Ooh. I don't think so. Wait, I think that's actually an NP hard problem. Yeah, so it's there's no practical. It's not practical to generate them all, and is considered exponential. So it's NP hard. So certainly not. I mean, you could brute force it, right? It's like worst case you can do is always consider what the worst case for any type of problem is, and then consider how hard that problem is, right? And so the worst case of it is to take all permutations of your different edges, and just make sure that your graph is connected, and then check to see what the weight of that is, and then you can find one MST, right? One MST is really not simple, but you know the algorithm for that, and then you just compare each and every permutation of your edges that creates a spanning tree, and then compare the weight of that to the minimum spanning tree, and if the same, then they're both MSTs, and then you just keep doing that for all of your different combinations, and you end up with some gigantic runtime, and we would not ask you to do that. Yeah, it's a very difficult problem. Yep. All right, let's move on. All right. So the difference between the two algorithms, know the difference between these black box algorithms. I believe they have the same input. They have different outputs. They run a little bit differently. And students love to ask, is there a difference between running cross-calls and prims? Generally, no. If you're using it as a black box, you generally don't have to care too much which one it is. You should name your black box. You can't just be like, run some unknown MST black box. You should name the one you want. It really depends on your output, but understanding how they work is really useful, especially with problems that start with a partial MST. So remember how I said, what if I just handed you part of MST and I said, I guarantee you that these are part of MSTs. What do you do on the next step? You would either do what prim steps are, or you would do cross-call steps. And knowing the situation, the differences between the two could prove useful for a problem that deals with partial MSTs. Know the cut property, super important. You will either see it as a multiple choice question. You will also possibly see it as, it could be very useful as part of your explanation of your MST algorithm. So if you have an MST algorithm and you know the cut property, you can say, oh, my algorithm picks this edge because of the cut property. And that's it. That's all you have to say, because we know what the cut property is. And if your reasoning behind your algorithm is based on cut property, that's all you have to say. If you forget it, you could also go out of your way to write out and do like a semi-proof of the cut property. I don't recommend that. That's really confusing. It could possibly hurt your grade if you don't do it fully. So just remember what the cut property is and use it. Optionally, learn the cycle property. We will also accept if you use the cycle property as part of your explanation. It's not covered in the lectures. I don't remember if it's in the book, but you can just look it up on Wikipedia. Basically, what it says is that if I have a cycle in my graph, the heaviest edge, the unique heaviest edge of a cycle cannot be part of any MST. Okay, and that is what the cycle property is. Learn it if you want to. If you don't, generally you can work around it, but I recommend it. Both algorithms will find an MST for an undirected connected graph. If we give you a MST problem, you can assume that it's undirected unless we specifically tell you it's not, which we will almost never do and probably won't. You can assume it's undirected, and you can also basically assume it's connected because a MST problem doesn't make any sense on a disconnected graph because there is no MST on a disconnected graph. But maybe we give you a disconnected graph and we say, add an edge somewhere to make this graph have an MST or something like that. But in general, you can assume, unless like there's a specific part of the problem that says it, you can just assume the graph is connected. This runs in all of m log n. And the way that this actually works, so the runtime for this is actually interesting. It's actually simplified. Let me see if I can pull up my tablet. I think I went over this a few weeks ago, but I should probably do it here. It makes more sense. Excuse me while I set up my. Should have done this earlier. I'm sorry. So for Kruskal's, the time it takes to run the algorithm, and actually prims, is actually the same as Dijkstra's. Okay, where is? Am I writing to the same one? Oh, okay. Just at the center. Okay. It's actually O of n plus m log. But because we know for a connected graph, m is going to be greater than equal to n, we can eliminate this runtime, this part, and it becomes O of m log n. And hopefully that's correct runtime. The other interesting thing about it is that this runtime is actually starts off as O of m log m, right? But we know that m is greater than equal to n. Therefore, we actually know that n is a tighter bound than m. So we want to try to reduce it to n if it's possible. And the way that happens is that because m is greater or equal to n, it's also true that n squared is greater than m. We can replace this m with O of m log n squared. And because log of n squared is actually m times 2 log n, this then simplifies. We can take away, for big O reasons, you can take away any constant multiplier. This ends up being O of m log n. And you don't leave it as m because we know that n is a tighter bound, okay? And that's the only reason why we do it here for prims and Kruskal's. For something like Dijkstra's, we keep it with n plus m because we don't know the makeup of the graph. But for MST specifically, we know the relationship, some relationship between our m and n. That should be okay. All right. But you don't really have to understand. Like, I think it's kind of neat to see how this runtime transitions down. But you don't really have to remember all that. You can just remember that, oh, I'm doing Kruskal's or prims. It's all m log n. Okay. So Kruskal's sorts edges by weight, and that's where your O of m log m comes from. It is using a sort algorithm, which we know is to be O of m log m, and then it grabs the lightest available edge that will not create a cycle when added to the MST. and then it does continues doing that. So another way to look at this is to never add edges if both endpoints are already merged, and then that's where the union find data structure is used. So go ahead and do that. Keep doing this until all edges that will not create a cycle are added. And that happens at exactly, this actually happens exactly when you have enough edges that's n-1, right? So once you get to n-1 edges added to your MST, there's no reason to continuously check all the other edges, because you know all those other edges are worse candidates than the MST you've already built, so you can just stop. And then Prims takes a different approach. What it does is it starts with an arbitrary vertex V, and you put it into a subtree S of included vertices. And then in each iteration, you grow S by adding the lightest edge between a vertex and S and all the vertices outside of S. Okay, and then you continue until all vertices are S. So this is very similar to Dijkstra's algorithm, because Dijkstra's algorithm uses this to find the shortest path. It's a little bit different, so be careful. They're related, but they're not the same. And Prims is actually a better demonstration of the cut property. It continuously makes wider and further and further cuts to show where those cuts are. Whereas Kruskal uses the cut property, but it makes those cuts anywhere on the graph it needs to in order to find the lightest edge. So you can, I think it's really good to understand both algorithms, because Prims shows you exactly how the cut property plays itself out. Kruskal shows you that the cut property can be used at any given point on the graph. It does not have to follow from any previous step. At any time, you can just cut your graph into two separate subsets of vertices and find the lightest edge, and then add that to your MST, and that's fine. That's what I have. Equin?
Hello.
Hello.
Hi. So, here you wrote down as m equals n-1, but in the, the runtime, like why m is bigger than n, or I thought incorrectly.
Yeah. So here I'm saying your algorithm ends the moment you have m edges. Sorry. Oh. Yeah, that's my bad. So this m is not related to the original graph. This m is related to your MST. So the better way to say that would be like, I guess, MST edges.
Oh, I
equal
see.
to n-1. Yeah. So like that's the number of edges we care to add to our MST. Once we have n-1 edges added to our MST, we are done. Any follow-up edges would only be greater or equal to the edges we've already considered, and so there's no reason to consider them anymore.
So the runtime O m log n, that m means the edges of the original graph, not the MST. Okay,
Correct.
got you.
Correct.
Thank you.
Yep.
Thank you.
Yep. No problem. All right, sorry for that confusion. Pierre?
Hey, Joves, can you hear me?
Yes.
So one question regarding the runtime for Kruskal. Given that, as we just said, m can be greater in the original graph, shouldn't the runtime be m log m, since you first sort the edges by weight?
Yeah. So that's why I did this little demonstration here. Okay. So we know that the sorting of the edges. Maybe we can try something. Okay. So things that we know that n squared is greater than m, which is greater than equal to n, right? So we know that moving from left to right, this right here is the tightest bound. We want to always use the tightest bound we can, but considering the worst case scenario. So even though m is greater than equal to n, we want to try to get to n, because n can be smaller than n, whereas m cannot be smaller than n. So that's what the definition of tightest bounds mean. Now, we start off by sorting the edges, which gives us m log m. Okay. There's no way to get from m to n unless you understand the relationship on this side right here. Okay. So we are going to basically take our m, push it to the upper bounds so that we can simplify it down to our tightest bound. And again, you don't really have to understand too much about this. I just want to show why that runtime is what it is. So we're going to replace m, and we say, well, on the worst case, m is n squared. So if we start on the data assumption, we can say, okay, m log n squared, right, is going to dominate okay. Now, if we work on this side, we can say, okay, well, we can simplify this to O of m times, because log of n squared is the same as 2 times log n. Okay. And because we're okay in normal, like, if we were just doing like math, actual math, we wouldn't be able to do anything with this. But because we're working with big O notation, and big O notation says, well, if you have a constant, you can just drop it. Like, it's okay. We're working on scalability. We're not too concerned about 2x, 3x, 4x, etc. So we can simplify this to be O of m log n, right? And therefore, this right here is a tighter bound than this, but we are only able to get to this n by replacing m with its worst case representation of n squared.
Okay, now
sense?
I get it. Yeah, makes sense.
Okay.
Thank you.
Great. Okay. So this is just the code for union find. I really suggest you go read this in the book. Look it up if the book is a little bit too wordy. It's a very well-known data structure, so you should be able to find all sources, sorts of sources for it. And so this is all from the book on how it works. Basically, what it does is it assigns some representation of each variable. Like, it'll say, okay, we are going to, and it has a rule on how to do it, but it says, okay, I'm going to choose a representation. This means that these two are have already been connected in Kruskal's. These two are already been connected in Kruskal's. These two have been connected in Kruskal's. And then it can say, okay, well, the second we connect, use an edge to connect another these two, we can put them under the same one to do to make them represented by the same same parent node. And then once you have that, then I know that if I was to say, oh, can I connect B? I have an edge between B and A. Should I connect them? I go, okay, well, what is my parent representing by B? It's D. Okay, what is my parent representing A? It's also D. Therefore, we are already connected through the eyes of Kruskal's algorithm. I should not include an edge here. Similarly, when I do G, I can add it here. And then once we find the edge, some union of B and G, so it's B and G. And the connection point is also represented by the parent. So like if you were trying to union B and G, you don't connect B and G, you connect their parents to each other, and that's how the relationship cascades down to the children. Okay, and that is how union find works. Okay. Okay, and then so strategies about looking for MSTs. As always, removing an edge or certain edges and then running the algorithm to determine what happens without that edge is a very common approach. This can work for Dijkstra's, DFS, BFS, and also in MSTs. So if edges are told, you're told some edges are special, maybe remove them, maybe do something with those special edges to change the consideration. Make changes to the weights to avoid some edges from being picked first. Make changes to the weights to force some edges to be picked first. Okay, negatives are allowed. You're allowed negative edges in an MST. Okay. Unlike shortest path problems, shifting all edge weights for MST problems is okay, because when you're looking for the shortest path, any change you make across all your edges is multiplied by how many edges a path takes. So if you subtract 1 from every edge, and there's a path that takes 20 edges versus a path that takes 3 edges, then 20 edges is going to be disproportionately impacted than the path that takes 3 edges. However, MSTs only care about 1 edge at a time. It only focuses on the lightest edge. So when you make changes, when you shift all the edge weights of your graph, they're still localized when they're being considered, and it doesn't affect. Now it's going to affect your final value of your MST, but you can just readjust that afterwards. The decision tree itself, I mean, the decisions made by the algorithm does not depend on multiple edges. It only cares about 1 edge at a time, so it's okay to do that. Be very careful when changing weights because you have to make sure you think it through. Okay, because there's a difference between being picked last and not being picked at all. If you take an edge and you say, I'm just going to assign it -infinity so that it will be picked first, sure. If you say, I'm going to take an edge and I'm going to assign it infinity to make sure it's not picked, that may not necessarily be true. If the MST algorithm has no other edges to pick, it will pick a edge with infinite weight just because it has to. So being picked last, which is what infinite edges do, and not being picked at all are two very different things. So be careful. So yeah, what happens if an edge weight is set to infinity? Okay, run goals or prims on the subset of G, and then build the rest of the build on top of that partial MST. So if you get a question like, oh, this MST must, I want the minimal spanning tree such that these following requirements are met, you might consider what to do about your graph to meet those requirements first, and then add the rest of the edges back to it. Okay, so that's one strategy to consider. Use the known MST properties, the cut property, the cycle property, and -1, etc. to justify your correctness. Don't try to reprove the cut property. The cycle property, if you need it, use it. Don't try to reprove it if you don't have to. Running crystals and prims with each edge removed and updated is a bad idea. Just like running DFS from every vertex is a bad idea, running dice stress from every vertex is a bad idea, running crystals and prims over and over again with edges removed is going to be a bad idea. It's going to be a really, really, really slow runtime. Okay, just don't do that. If you start with an MST, if we give you an MST and we say, oh, we want to make a change to this MST because we change one of the edges, or we change one of the vertices, or we say that we no longer allow this edge. If you come back to us as, oh, I'm just going to run crystals for prims all over again, you're going to lose a ton of points. That is way too simple of a solution. It doesn't show any understanding of prims or crystals. It doesn't show any understanding of what MSTs do. You're just basically giving us a brute force solution at that point, and you're going to lose a ton of points. So don't do that. You can run crystals or prims as your first step if you don't already have like a structure of an MST. But if you're given an MST and you want to update it, there are faster methods than rerunning the entire algorithm. Okay. Mahmoud?
Yeah, sorry. I don't know why my brain didn't really connect with what you said last. So could you re-explain what you mean by if you start with an MST and there's a change in one of the edges running crystal? What do you mean by that? Sorry.
So if I told you I had an MST, right, and I said, okay, all the here is an MST. We've established an MST.
Okay.
But for some reason, I made a mistake. I made a mistake and I added an edge that isn't actually in my graph. I added an edge between A and B into my MST. I know the rest of my MST is correct, but I added an extra edge by accident. Can we fix this MST? A question like that requires you to only consider the cut that is reformed after removing the edge. It does not require you to build the entire MST from scratch. And if you build the entire MST from scratch, it's going to be a slower runtime than fixing that MST. So don't do that.
Okay. And then my other question was, I know we stated that it's okay for us to make changes to the weights and edges, but I'm trying to comprehend why that would be like a useful strategy. I know that you said, for example, -infinity and +infinity to kind of like have an edge be selected first or it's not selected at all, but Could you go a little more in depth into that? Like, what would be another reason why you'd want to shift or change the edge weights?
Let me check something real quick. I want to make sure I am correct in what I am about to say before I say it. Okay, I would say you should take a look at homework 8 for an example of perhaps such a strategy.
Gotcha. Okay.
Okay.
Thank you.
Yep. All right. Common mistakes that students make. Again, this is not the weight of these mistakes. These are how often I see these mistakes. And of course, these have shifted since I've started pointing them out. There might be less than they used to be, but these are common mistakes students make when they first start doing the homework. Suboptimal solution. Again, this is one of our more common issues. I think less so in graphs, I would say. In graphs, because you're basically forced, almost like, not forced, you're almost like pushed into using a black box. The suboptimal solution doesn't happen as much for graphs as it does with divide and conquer, and then happens in divide and conquer all the time. Actually, that's probably our most common penalty. Okay, so for the algorithm side, modifying the black box, just like any of the other graph problems, do not modify the black box. You are not allowed to for this topic. Doing that is, a big penalty. Runs an MST algorithm from scratch. If you are provided an MST and we want you to update it, do not just run the MST algorithm from scratch. This is a very big penalty. It shows very little understanding of the topic, and so this is a very big penalty. Don't do it. Algorithm results in an MST, so you go through your steps and you try to build, an MST that fits the requirements of the question given to you, but you end up breaking one of the properties of MST. Maybe you have too many edges. Maybe you created a cycle. Maybe you didn't pick the lightest edge, so that can happen. Algorithm doesn't actually solve the problem requirements. So you're given the problem, you said, I want you to build an MST that fits the following requirements. If you skip those requirements or miss it, that's a penalty that can happen. And that does not provide all the inputs to the black box. Know what the black box takes in. I think MSTs is just an undirected graph with a list of weights for every single edge. No source. Yeah. So those are just know what the black boxes are taking. Sometimes you will need to do connectivity with MST problems. Students used to have a tendency to use DFS for connectivity checks by using the visit array, and we had to constantly remind students that it's not what the visit array does, and you're going to get it wrong. So just don't use DFS for connectivity checks. I think it's a bad algorithm for it anyways. You can, but you have to go extra steps to explain it, and I just wouldn't do it. Correctness justification. Yeah, so a student says that the visit array is inaccessible. We made it inaccessible. This mistake was so often that we stopped letting students use the visited array as an output, because it gives you no information and students wrongfully assumed it does. So we just took it away. That was more for your benefit than it was for our correctness justification. You don't explain why edges are removed, added, or modified. If you modify your graph to build the MST, you have to explain why you modified the graph, or explain why the MST is still valid after input modifications. So if you make adjustments to the graph and we give you a problem statement, you also have to echo back to us why you can still build an MST from your modified graph. Because if you remove too many edges and you can no longer build an MST, that kind of defeats the purpose of the problem. Does not explain how the output solves the problem. Like if we ask for a requirement, you have to tell us why the output MST solves that problem. And then runtime analysis, the usual, giving the wrong, incorrect runtime, minor mistake, or so we no longer do this. This is actually something we take away. We used to expect students to simplify their runtimes based on what they know about the graph, and it was very much a thing for MST problems. But I believe we no longer require this. We have taken that out because students were getting confused from it. So if you know the runtime of a black box, just go with the runtime of the black box. That's all you need to care about. That being said, if the runtime of a black box is given to you, and it's a well-established runtime for the black box, don't come back to us, give an unsimplified version of it, and argue that you didn't have to simplify. That's not going to work. So if I tell you that the runtime for MST algorithms are O of m log n, and you give me Dijkstra's runtime, and I tell you, well, actually, Dijkstra's runtime and the runtime of MSTs are related. However, MST black boxes simplify that runtime for the following reasons. And you come back to me and say, well, you said not to simplify. That's not the same thing. You didn't fail to simplify. You unsimplified a known black box runtime. That's not okay. All right. Any questions about MSTs in general? Let's see. Bing.
Hey, thanks, Joves. I have a couple of questions. First, when you say modified black box algorithm, I want to ask you one example. So if I change the weights of certain edges before feeding that into Kruskal's, that's not considered a modification to the black box algorithm, right? But if I change how the sorting works, so certain edges are sorted after certain other edges, then that would be considered modification.
Correct.
Okay.
That's correct.
Okay, that's great. Okay, the other thing is sometimes the questions are not very clear if the edges are directed or not. How do we tell? Like, for example, homework 8, I read it many times, and the only clue I saw was the word between. That seems to indicate that the routes or edges are undirected. But if it's in the exam and it's not very clear, what's the best way to proceed? Should we make the assumption and state that, or should we actually assume it could be either and handle them differently?
I would say that if you come across a situation such as homework 8, go with the one that makes the most sense to you. I don't want to say like, oh, always go with undirected or go with directed. To me, when I read the problem for homework 8, you're given a route that can travel between homes. That it implies that you can go in either direction.
Right. It's the word between that gives him that that kind of feeling. So when I first saw that this morning, I immediately feel like it's an MST problem. And then later I was like, oh, what if it's directed? And then I just looked everywhere. Then I became a little uncertain and spent at least half an hour just thinking, what if it's directed? Then how do I solve this problem?
We will be extra careful on exam problems, but for something like this, you can probably just ask in the thread and say, hey, are these edges considered directed or not? And
right.
TA will answer it.
Okay.
Yep.
Okay. Thank you.
Yep. Mahmoud?
So I might have missed it, but there was a question in the chat, I believe related to MSTs where one person asked, my understanding is that is the same SCC implies there is already a path between two vertices. If you add another edge that connects them, you get a cycle. And after that, someone replied, an SCC should have a cycle in it. If there are two vertices in the SCC, no. Every vertex in the SCC is reachable from others in the SCC. I think this is related to like how the tree is connected and how you can solve for how you solve Kruskal's and Prims. I'm not quite sure.
Okay, so
if anyone wants to
few
like
things.
jump in and
No, I
brainstorm.
see the question now. Okay, so first of all, SCCs only matter for a directed graph. MSTs only matter for an undirected graph. So the two topics are almost in all cases exclusive from each other. You're never going to talk about SCCs in the MST problem. You're never going to talk about MST in the SCC related problem. So that's one thing. Everything within an SCC is in a cycle. So yes, that is a true statement. Everything that's in the same SCC can reach each other. That is what the definition of the SCC is.
Okay, thank you.
Right. Yep. So if you're like thinking, oh, what do I do about SCCs in the context of MST? You don't. They don't. There's two separate problem sets. They're not going to be related. There could be a problem that's like, oh, if I, yeah, I'm just going to say that they're not related. I don't think there's any problem I can think of that's like ever crossed that boundary between the two. They just work on different graphs in general. Yep. Okay. Swing Kai.
Hi. Could you give an example of the third mistake in the algorithm part? I assume that if we use the black boxes, how can we end up with an invalid MST?
Yeah, so you can't modify the black box, therefore you can only modify the input and output. So if you modify the input such that an MST is not possible, then your black box is just going to be like, I don't know, and not give you a MST. But if you also take the output and you do some changes to it and you break your MST that the black box gave you, that's also giving me an invalid MST. Or you build a partial MST and then you go and you want to add additional edges to the MST for some reason, and you add those edges wrong, that can also result in an invalid MST.
Thank you.
Yep. Bing, did you have another question?
Yes, I do have another question. Sorry. So you said don't use DFS to check connectivity, like if the graph is connected before MST, right? Like the homework problem tells us it's connected, so we don't have to check. But if it doesn't say we need to do connectivity check first before generating MST, then in that case, what's the recommended approach? Or should we just do something like BFS and then check either the
I use
distance or
BFS.
Okay.
Yeah, I do BFS from some source and I check the connectivity to other vertices via the distance array. And yeah, I mean, the whole point of building an MST is to make sure all vertices are connected, right? So there might be a problem out there that you need to know if vertices are connected in some way before you want to take an action. So it is a useful tool to take. Useful thing to do is to check for connectivity, and some students do it wrong because they use DFS instead.
Right. So is that correct to say if a problem doesn't tell you it's connected and it's an MST problem, we should always check connectivity first?
No,
because it may not be feasible.
I think if we give you an MST problem and we don't tell you it's disconnected, you should assume it's connected. I think that's a fair assumption. Yeah.
Okay.
Okay. Yep. I'm going to answer one more question, and then I'm going to allow for a break before we get back on to learn about max flow problems. Shanek?
Hello, Joves, am I audible?
Yes.
Quick question. I joined late, so I apologize if you already mentioned this. But if we use DFS to check connectivity, then in that case, can we go by checking if CC_num is 1 or not, and using that to interpret connectivity?
Yeah, you can. I wouldn't suggest it. It's easy to mess up, and it's harder to explain. So if you want to, if you're like, oh dang it, I'm going to use DFS no matter what, then yes, you should use DFS and then check if the two vertices are in the same CC, have the same CC_num, because if they're not, then they are they're disconnected, or there's no path between them.
Okay. And if I may ask, like, why do you say it is more complicated to check connectivity with DFS as opposed to BFS? Because I assume even with BFS, we have to scan over every vertex to see if the distance is less than infinity to know if it is connected or not. Or am I missing something?
Because you generally want to check whether two vertices exactly are disconnected or not. So like you're basically saying, oh, can I get a path from S to V? And so you run BFS from S and you say, is V's distance infinite or not. And so that's a very clear, thing to do in my mind is like I do it from S because I care about if I can reach V from S, and then I check V specifically, and that's it. When you do DFS, there is no source, right? You just run DFS, and then you say, okay, well, is my source vertex and my target vertex in the same CC num or not? And you have to understand what CC num is. You have to understand what connected components are and why connected components don't have the same number that's disconnected. Like if you feel comfortable doing that, by all means, do what you're comfortable with. But as a recommendation for myself, when I say, oh, you should just do it this way. It's simple. It's understandable. I'm thinking of like all the students out there that are like, oh, what is the simplest way to do something? And to me, BFS checking for connectivity is just the simplest way.
Yeah, I'm sorry. I just wanted to understand your context, but yes, absolutely. What you say makes sense. Thank you.
Yeah. And one point that one point to consider is that when I said use BFS to check for connectivity, everybody understood. But you had to ask me, if you use DFS for connectivity, is this the right way to do it? And so like the fact that you had to make that additional leap tells me that's a little bit more complicated than when I just said use BFS and everybody knew what to do. Just
okay. Yes.
Yeah.
Thank you. Yes.
No problem. Akmal, last question.
Can you hear me?
Yes.
So just a quick question on BFS on the dist array. I know that dist array, you use BFS when you're not like it's not a weighted edge. So in this case, in dist array, does the dist array, what does it return? Is it returning like the number of edges that you're away from your source?
Yeah, if you run BFS on a graph, it's going to be the number of edges from source to all other vertices.
Okay, and because with Dijkstra's, it's more about like the number, like the sum of the edges from starting. But with BFS, it's the number of edges away from starting. Okay, all right,
Right.
thank you.
Yep. Okay, I am going to take about 2 to 3 minute break and then come back and we're going to do Maxwell. So, right back. Still got a couple minutes.
Jovis, sorry, I wanted to ask a question real quickly because I didn't realize this was possible. If I run DFS on a unweighted graph, it just assumes that every edge is a weight of 1 and it just calculates the distance as if it's like how many nodes away it is from certain S?
For BFS?
Yes, sorry, I should have been more specific. BFS, yes.
Well, yeah, because when you run BFS on a weighted graph, the weights are a separate array, and there's no input for that. So a BFS run looks at a graph and it's just not going to know anything about the weights. So it just acts as if it's an unweighted graph.
Sorry, I'm a little confused there. If I have a weighted graph, BFS will use those weights to calculate the distance
No,
from.
it will not. Right. So BFS takes in a graph made up of vertices and edges and a source vertex. Right.
Okay. Yeah.
If you have weights or lengths or distances, whatever your array is, BFS just doesn't have that in its input. It just doesn't know about it. Dijkstra's has the input of a graph, a source, and a weight or a distance array or length array, whatever you want to call it. So in its input, it'll say, what are the lengths of these edges? And then I will calculate distances based on it. BFS algorithm doesn't even have that as its input. So it's never going to know anything about those lengths or weights. It's just going to calculate it as if it's an unweighted graph. They're like completely separate data structures.
Okay, I think that's where my confusion was. I thought there was supposed to be a weight needed for that, but I guess not.
Nope.
Thank you.
BFS does not consider weights at all. It just treats each edge as a single unit of distance.
Understood. Okay, thank you.
Yep.
Jovis, can I ask a question or no?
Absolutely. Go for it.
I know it's break time, but can I ask or should I wait?
Let's give it. Let me give people one more minute, and then I'll let you ask the question.
Okay, because this is a bit irrelevant to what we were talking about. It's about how we can like do better in the second exam.
I'm gonna wait until it's 3:51, and then I'll let you ask that question in case anybody wants to hear it, and then I'll answer it.
Sure.
3:51. All right, go ahead. Ask your question. I'll try my best to answer it.
Okay, so for the second exam, I was thinking, Jovis, that because a lot of us, including myself, like lost a lot of points for writing suboptimal algorithms. What I'm thinking to do, avoid that mistake in the second exam, what I'm thinking of doing is that are two things, to consider two things. One, when we're writing an optimal algorithm, we need to consider what type of problem it is and what it's asking. And based on that, we have to consider what will be the asymptotically lowest runtime that can be achieved. And we can write that algorithm that certainly meets that runtime, asymptotically lowest runtime, and make sure we don't write anything that makes the runtime go higher. That's my first thought. My second thought is it's not enough to just write an algorithm that is correct, that solves the problem correctly. It must also be optimal. Am I making sense, Jovis? Those are my two trains of thought that came to my mind on how to do better on the second exam and to avoid that mistake we made on the first exam.
Yeah, I mean, algorithms is all about getting the correct answer as quickly as possible. Like the entire idea of algorithm is surrounds the idea of I need to get the right answer and I need to do it as optimal as possible. So it's two parts. It's never, oh, if I get it correct, it's almost there. Like it's basically two vectors that we are going to grade on, and they don't even both the penalties for both don't even sum up to only 20 points. Like if you get a really poorly optimized algorithm, you can lose a lot of points. And if you get an algorithm that's very, very wrong, you can lose a lot of points. And both of those are more, the penalty for each of those are more than half of the problem. Because we want you to understand how to solve a problem and how to solve it efficiently. Because not just in computer science, in everyday day-to-day software engineering, you can write code that solves a problem really poorly. I see it sometimes, and it's not good, right? Like for most users, if they don't get like if they don't get a solution, or if they don't see a response to their to their requests, like what they perceive as fast enough, you might as well not have given them an answer, because they're going to be just as upset. And so that's just the way it is. I think yeah, knowing that you need a optimal runtime is very important in this class.
Right. That's why I thought, right? So one, it's not enough to just write an algorithm that solves the problem correctly. It must also be optimal. So basically, what we write must be both correct and optimal. That was my first thought. And the second thought, shoot for the asymptotically lowest runtime possible and write that algorithm that certainly achieves that asymptotically lowest runtime.
Yeah, I think we're hoping that through practice and through the office hours and all the material that you're giving, that you recognize, even if you don't know how to solve it, we want you to be able to recognize what the fastest runtime is first, and then be able to work towards that runtime. Like generally, that's idea, because knowing how to solve a problem, especially with the with all the different problems we give you, I think is actually the easier part, especially divide and conquer. For divide and conquer, solving the problem is not hard. It's by far the easiest part of the algorithm. Solving it efficiently is where all the all the value of divide and conquer is.
Okay, so
and I think
basically,
that's a problem that most students got caught up on, right? Is the solving the divide and conquer problem optimally. I don't think I saw many students get tripped up on the on suboptimal solutions for the dynamic programming. And that's that's what I told students to expect going into the exam, that actually solving the problem for dynamic programming is the hard part. Solving the problem efficiently is the hard part of divide and conquer. So keep that in mind going into the exam. Okay.
thanks, Joves.
Yep. Time to cover max flow. If MSTs is my favorite part of this section, max flow is my least favorite part of this section. I don't know what it is about max flow. I just don't really enjoy these problems. But hopefully you enjoy them, and that's all that really matters. All right. So max flow problems are networks. We're dealing with a directed graph, so they have to be directed because there's a flow. The flow has to be in a direction. So if you're ever given the max flow problem, assume it's directed. There are going to be two special nodes in most cases. In the general max flow problem, there's going to be a source and a sink. This is different from the SEC and graph source and sink. In this case, source, I mean, they're kind of related, but all flow starts from a single source and all flow ends in a single sink. There are some variations of the problem that are going to say, oh, there are multiple sources or multiple sinks. But in general, if you're giving a generic max flow question, there's going to be one source and one sink. Okay. And the capacities of all the edges are going to be greater than 0. They are not going to be 0 capacity, because 0 capacity doesn't mean any. That means that the edge doesn't do anything. So that's kind of useless. And negative capacity makes no sense. So all edges are going to have positive capacity. Okay. Our goal is to send as much flow from the source node to the sink node. We want to maximize our flow. We also have to satisfy some properties. So your final answer, your final flow, has to follow a few properties. One, you don't violate any of the edge capacities. You either have zero, you either have less greater than equal to zero, sorry, your flow is greater than equal to zero and less than equal to the capacity. You cannot go over capacity, and you cannot go under zero flow. For any node, except for the S and T. So S is considered to have infinite outgoing flow, and T is considered to have unlimited incoming flow. But for all the other intermediate nodes or vertices, the flow coming in must equal the flow going out. You cannot send more flow into a node than the node can handle coming out of it. Okay, so it has to be equal. The flow is conserved. Okay. The size of a flow is the total quantity sent from S to T. So when we say what is the maximum size of the flow for this max flow problem, it means how much can I send from S to T by the conservation principle. And so anything leaving S is equal to anything coming to T. There are variations of this problem that might break. So all these assumptions you should be made unless told otherwise. We may be able to modify the way that the max flow works based on the wording of the problem. But if you don't get told otherwise, these are the assumptions you can make about the max flow problem. Okay. So here are some diagrams. This is what a typical max flow diagram looks like. You have your pen. You have your source, you have your sink, and then you have these edges that all have capacity. So from S to A, there's 6 capacity. From A to D, there's 4 capacity, so forth and so forth, and all the capacity listed. Okay. This is what the final flow or a possible solution to our max flow is. And this green is how much flow is going through this edge, and the red is how much capacity there is. So here we are sending 6 out of 6 flow from S to A, 1 out of 1 to B, and 6 out of 10 to C. And that's what all these other numbers represent. Here is 4 out of 4 from F to T, and 9 out of 12 from G to T. Note that this number, which is the flow, will always be less than or equal to this number. And that it can also be 0. You can send 0 flow down a edge if you want to. That's fine. That's allowed. But it cannot be a negative flow because that doesn't have any make any sense. Okay. And if this edge has 0, let's say this edge had 0 capacity, it might as well not exist on the graph. There'd be no reason for it to exist on the graph because it doesn't do anything for a max flow problem at all. Okay. This is what's called a residual graph. So this residual graph matches this flow graph. And what it's saying is that a residual graph has what's called back edges. It means that in order to change the flow a little, I am allowed to send flow back the other way. So if I have 6 out of 6 coming from S to A, if I wanted to readjust my flow so that I can send flow elsewhere, I can send 6 of that flow back. If I send 6 flow back from A to S, this changes to 0 out of 6. Okay, and so every time you have a flow, you end up being able to draw this residual graph that gives you all the edges that kind of acts as a capacity on the next run of your max flow algorithm. Now, notice how here I have 4 out of 5. How does that look on the residual graph? Well, I have 1 flow that I can go from D to G. That's what this 1 represents. And if I have to, I can go on the back edge from G to D with 4 flow. I can send 4 back because I have 4 coming, and I have 1 more capacity that I can send from D to G. So that's what this 1 and 4 represents. Okay. I think the book or lectures will talk about parallel edges and how those are all those are handled. You generally don't have to think too much about them. We don't really use them. But if the reason why you have to handle parallel edges is that if there's an arrow from D to G and there's already a arrow from G to D, then that messes up this residual graph layout, and so you have to create like this this intermediate node to handle this parallel edge, but don't understand it, but we don't use it too often. Mabu, question? Hold on. Do I have one more? Okay, go.
I haven't fully watched the lectures yet, so maybe this question's already answered. But max flow diagrams should not have cycles in them, as far as my understanding is correct. I don't know if it is. Right?
I think they can, but I don't think it's useful. Trying to think, is there anything that explicitly disallows a cycle?
The BECF in this picture is a cycle. So I think the professor explicitly said it's okay to have a cycle.
Yeah, I want to say it's allowed. I don't recall anything that that causes a cycle not to be allowed. So I think you can allow for a cycle. Yeah. And actually, you absolutely can have a cycle because I literally just talked about parallel edges, and parallel edges only exist because it is a cycle, right? So if I had a edge from D to G, and I have an edge from G to D, and I said, oh, I have to specially handle this parallel edge, it's because there's, not because there's a cycle, but because I have to handle parallel edges, and if parallel edges are considered, then cycle must surely be allowed because that's what a parallel edge would do.
Right. Okay.
Yeah.
Sorry.
Yep.
Thank you.
Yep. No problem. Shanak?
Hey, Joves, quick question. So you mentioned about the parallel edges earlier that we cannot allow them because it will create complications in the residual graph. So if we are given a max flow problem, are we supposed to search for parallel edges and remove them before applying Ford-Fulkerson or the others?
I would suggest that Ford-Fulkerson as an aside handles the parallel edges for you. I wouldn't like call it out explicitly. And I'll check with the TAs on that. I'll just say, hey, I really don't want students to have to say handle parallel edges at the beginning of every single max flow solution. So we'll just not deal with that. You should understand why it needs to happen. I think that's important, but I wouldn't say yeah, you're given the max flow graph, make sure there's no parallel edges, otherwise you'll lose points. Like that, I think that would be messed up.
Okay. Thank you.
Yep. All right. So moving on. So ST cut, not the same as the cut property. So you just have to learn another word. So the general word cut means to divide up your vertices on a graph in such a way that everything is is either on one side of the cut or on the other side. And it's also not really truly like a side, because you can basically drag A all the way to this side and drag G all the way to this side, and make your cuts differently. But a cut is just a way to divide up a graph. That's what it really is. And there are some properties that make use of it. And here we care about what an ST cut is. So an ST cut partitions the vertices into two disjoint groups, L and R, such that S is in L, T is in R. This capacity is the total capacity of the edges from L to R. And as argued previously, is an upper bound on any flow. Pick any flow F and any ST cut LR, then size of the flow is less than or equal to the capacity of LR. Well, that's a lot of words to mean. So basically, you cut your graph in such a way that your S is on one side, your T is on the other side. And then you sum up all the edges that goes from the left side, from one side to the other, right? From your S to your R. You don't care about edges going from R to L. You only care about edges going from L to R. That creates at least one, at the very least, an upper bound to what your flow is. Because what you're saying is that if I have this cut right here and I want to send all my flow from the left side to the right side, I cannot exceed the capacity of this cut, because that's all the flow I have going from one side to the other. And this is true of every single cut you make on your graph. So if I make any cut here, 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 etc. All these cuts, no matter what, I cannot send more flow from S to T than any of these cuts would allow. Okay. And it is the minimal of these cuts that we are interested in, because the minimal flow determines what the maximum, so the minimum cut determines what the maximum flow we can send through our flow diagram. Okay. So here's a cut, here's a cut, here's a cut, here's a cut, right? Remember when I was making cuts of MSTs and I was like, oh, I'm just going to isolate a single vertex as a cut. You can do that. You can have any number of vertices as long, as a subset of your cut. Okay, that's a cut. These are all cuts. And then so once you have a cut, right, you can calculate how much flow is coming from the L cut to the R cut. It's only the outgoing edges that matter. So here we have this outgoing from L to R. This edge is a 6, 1, 2, 4. So this cut has a capacity of 13. Okay. This E to F doesn't matter. Not when we're calculating capacity from L to R. Any incoming edges doesn't matter. Now, any edges going from the same a vertex to another vertex in the same cut also doesn't matter. So this S to C, we don't care about how much flow there is. We only care about any vertex who is on the left side going to a vertex on the right side, and we sum that two up, and this is 13. This happens to be one of our minimum cuts. So if you look at the solution, coming out of S is 6 plus 1 plus 6 is 13. Coming into T is 9 plus 4, which is 13. Notice how over here from this cut, I still have more capacity. I have 3 more capacity. Notice how coming out of this cut, I still have more capacity. I have 4 more capacity. But my minimal cut, which only has 13 capacity, means I can't push past 13 flow, and that is what determines my max flow is. Okay, so your max flow is equal to your min cut, right? And this is the theorem. The size of the maximum flow in a network equals the capacity of the smallest ST cut that you can make. A graph can have multiple min ST cuts. Okay, that's possible. Because like if a really simple way to look at this is like if I have an S and I have a T, and I have an A, and this is 5, and this is 5, and I can only send 5 flow. This cut is a minimal cut. This cut is a minimal cut. You can have multiple minimal cuts. It just means that capacity cannot exceed the flow cannot exceed the capacity of that cut. And so if 5 is the maximum, then I have multiple cuts that have a capacity of 5. Each of those are considered a minimum cut. Yeah, and then this is just a statement that because the min ST cuts, you go to your max size, right? Any cut, right? Any other cut must be greater or equal to your minimum cut. If you have a minimum, everything else is greater or equal to it. Makes sense. If you have a maximum flow, everything else is less than or equal to it, which also makes sense, right? So this is the single statement that unifies all of this information. Okay, Robbie.
Thanks, Joves. Just so I understand, when you were doing that max cut from 6 to 1 to 2 to 0, 6 to 4, you were counting the outgoing edges, right? For any cut, don't we have to also take into account all the incoming edges that are going into that are going in?
You do not. You do
because
not.
the lecture notes had mentioned it, and I believed it.
You care about the incoming edges when you calculate when you run like one of the max flow diagrams. The incoming edges certainly can allow you to move flow around. But once you've identified all the, like if you identify all the cuts and you check all the capacity of every single cut, there's going to be a lot of them. It's a suboptimal way to do it. But if you identify all your cuts, check all the capacity, you only care about the outgoing edges from one side to the other, and that will be able to find the minimum cut, which gives you the maximum capacity.
Okay.
Yep.
Let me think this out. Thanks.
Yep. Last bullet point again. right, so if you believe me when I say the min SD cut is equal to the max flow, hopefully that part makes sense, then any flow, any intermediate flow, when we say intermediate flow, we're saying as I am going through my algorithm to find my maximum flow, I try different flows. I try sending different amounts of flows through my float network to get to that maximum flow. Those intermediate flows can never exceed your max flow, right? It makes sense because the moment I can send more flow into my flow diagram that exceeds my max flow, then I have found a new max flow, right? So you can never exceed the max flow on any valid flow. Okay, so any intermediate step of throughout your diagram can never exceed that max flow. The other part of it is saying that I'm going to cut my graph into multiple cuts. If I have a minimum cut, all the other cuts cannot be smaller, because if I have a smaller cut, that would now be the restriction of my flow, and that would be a new min cut. There will be other valid cuts, certainly, but those valid cuts has to be greater than or equal to my minimum cut. They can be only nothing can be smaller than minimum, nothing can be bigger than the maximum. Okay. Eduardo?
Yes, hello. Can you hear me?
Yep.
Okay, so just looping back on the definition of min ST cut, does that apply to any cut we want? Or so for example, if I cut S to A, is that defined as min ST cut, or does it have to be a cut from S to T, which is equal to max size F?
So when you do a cut, you can only have two subsets. So you can't just cut S from A, right? Because that's like two
Right.
vertices. All the other vertices have to be considered. You can cut S from A, B, and C. That's a valid cut. Or you can say, I want to cut S and A together. But what you cannot do, not when we're considering ST cuts, because it's in the name, right? We're cutting S and T. You can't do something like this. You can't just carve out D by itself and then S and T is in the same cut. That's not something that you can do because it doesn't have any value, right? The only thing you care about is cutting S to one side and T to the other. Now the most isolated cut you can do is this one. That's a valid ST cut, right? S is on one side and T is the other. And then this is also a valid cut, isolating T by itself, but you cannot have S and T in the same cut for an ST cut.
Got it. Thank you.
Yep. Okay. So you have your two max flow algorithms. They all take in the same input. They take in G and then a source node, a sink node, and C represents capacities. Okay, also known as the float network. So the entire input is called the float network. So if you don't want to type this all out, you can say, pass in the float network to my algorithm. Like you might have to establish what each of these things are, but you can just say I'm going to pass in the float network, and that's understood to be the graph, the S, T, and the C. The graph is directed. S is the source vertex, T is the sink vertex, and then C is capacity such that the capacity is greater than 0 for all edges in my list of edges. Your output is F star C. Okay, what's this mean? F is, you can look at it as a function or a vector, however you want to look at it, but it's a way to look up the flow of a given edge. So F of UV is the flow of this edge. Okay. It is updated as the algorithm runs. So as the algorithm runs, it keeps this function or vector or array, however you want to look at it. It's not really important what that data structure is. It'll keep updating it. And this is why I say a valid flow. A float network can have many, many valid flows. Valid flows just means that I am going to send flow from S to T, and I don't break any rules. max flow is my ultimate goal, but there's a lot of valid flows before I hit max flow, right? Like if you just turn on the water source at the very beginning, it doesn't go from 0 to max flow immediately, right? The water trickles down, and as it's doing that, it's all valid until it hits, as you move towards the max flow. F star is what we say is the max flow at the end. So once the entire algorithm runs, we are given an F star. This is a max flow across G, and this is still a function or a vector, and it tells us the flow of all our edges when our flow network is maximized. And then we say that the thing we're trying to maximize is the sum of all flows of all edges attached to T. That's what this means, okay? So the summation of the flow into T is what we're trying to do. We're trying to maximize that. I think we call this flow. I think Jamie uses a different terminology when he writes the black box. Let me see what he says. Just double check. Yeah, he gives a flow array or list of edges representing the amount of capacity. So use that if you want. I think it's either's okay, but go with that since it's in the post. When we say what is the size of that flow, then that is the numeric value of the flow calculated. So this flow that I'm telling you right now, such that this is maximized. When we say what is the size of that flow, we're looking for how much flow is coming into T at the end of our max flow algorithm. And this is also known as C. This is the capacity of our max flow, the overall capacity of what our float network can take. Okay, this C is important because it's a way for you to represent what that max flow is, but it's also used in the runtime of our one of our algorithms. Okay. Now, the other interesting thing about Ford-Fulkerson versus Edmond-Karp is that Ford-Fulkerson isn't a complete algorithm. If you look it up, if you look up the history of Ford-Fulkerson and Edmond-Karp, Ford-Fulkerson is a template of an algorithm. It basically says, here's what you do to find the max flow, but it leaves the detail of how to find a path between S and T out. It doesn't actually say it's DFS. The assumption is that it's DFS, but it's actually undefined. Edmond-Karp comes along and says, oh, I can actually get a better, a more specific runtime by saying the path finding algorithm is specifically BFS. Ford-Fulkerson doesn't, and therefore it's left for others to find. In fact, the Ford-Fulkerson template has been used to get a better max flow runtime than Edmond-Karp. It basically follows the very same structure, but there's different things that it does. I forget what the other algorithm is called, but for this class, we only care about the Ford-Fulkerson and Edmond-Karp setup. But the algorithm basically says, okay, we're going to set our flow to 0 to start. Right? We have to initialize our flow array to something. We're going to initialize it to 0. No flow has gone through. We're going to start by building a residual network. And when you do any max flow type algorithms, you can say build a residual network as a step. You don't have to go through like the nitty gritty details of building a residual graph. Let me just see what we say here. Do we really not say anything about residual graphs? Or is that part of the output? Yeah, I would say that building a residual graph is something you can just say you do. It's kind of like, oh, I want to reverse the graph. It's just a step that you can give without having to give the full details of it. Okay, so then you build a residual graph. You check for any path in G from S to T. So remember how I showed you that residual graph and there's edges going forward and going back. The reason why we need the back edges is because when we look for a path from S to T, we are allowed to take those back edges in order to find that path. And if we can find a path, what that basically means is like, oh, I send flow down this edge, but if I move some of it back to backwards, I can send that flow to another less saturated edge, and that will increase my flow. So that back edge is important in trying to find the path between S and T in the residual graph. Okay. You can use DFS or BFS for this. If none is found, we're done. We cannot send any additional flow through our float network. We have found our max flow. We are done with our algorithm. However, if we find a path from S to T in our residual graph, we're going to walk that path and we're going to say, what is the minimum capacity along this path? We're going to assign it a value. And then we're going to augment that entire path with that many units along the path. Basically, I find a path from S to T. Each edge has different remaining capacity, 4, 5, 6, 7, 8, whatever. And I find, oh, my minimum remaining capacity across that path is 2. So I'm going to send 2 units of flow through that path to get a higher flow than I did before. So I have increased my overall flow by 2 units. Yeah, so you increase the flow from U to V by this many units, and then you update the residual graph. You run the residual graph part of the algorithm again. So for each forward edge UV, so every forward edge that represents capacity, we decrease the units because we are taking away capacity, right? So if I show that I have 4 capacity and I want to use up 2 of those capacity, I'm going to subtract 2 from the forward edge to show that I have 2 less capacity in the forward edge. For the backwards edge, though, we increase by that many units because that's how many units I can take back through my back edges if I have to. So if my initial flow on a forward edge was 0, and I said, oh, I'm going to send 2 capacity forward, I subtract 2 from the forward edge and I add 2 to the back edge because I am allowed to go 2 units backwards if I have to in order to find a path. Forward edge plus the backward edge, so the two capacities added together is equal to the overall capacity of the edge because I have to maintain that overall capacity number. And then you recurse to step 2 and you keep running this until you have found no more paths between S and T in the residual graph. And at that point, you are done with your max flow algorithm and you can output the solution. Okay. Questions about this template of max flow algorithms? Eduardo?
Yes, thank you. So in step 4, we're saying if found, get the minimum capacity. Why would it be the minimum and not, for example, a maximum, since we're trying to maybe maximize the flow that goes into T?
Yeah, so you have found a path, right? So like you run some amount of recursions of this algorithm, and then you found a path from S to T, right? That goes through A, that goes through B, that goes to T, right? And I have 1, 2, and 3 that's left. This is the remaining capacity of my edges, right? How much capacity can I send down this path to increase my flow? If you do the maximum, you say 3, but I can't send 3 from S to A. I only have 1 capacity left. I can't send 3 from A to B. I only have 2 capacity left. So you take the minimum, which is 1, and now I update all of my forward edges to be 0, 1, 2, right? Because I can send 1 additional unit, and my flow increases by 1. That's why you have to use the minimum number and not the maximum.
Got it. Got it. Thank you.
Mahmoud?
So just to clarify, this is the template that we use when we're running Ford Fluckerson or Edmund Karp, but we don't have to specifically state this when we just say run this and it should just work. But it's good to know this for our justification purposes. Is that the purpose behind this slide?
It's good to understand the black boxes you are using. So everything we teach in graphs, we are going to explain to you. So I like to think of our the way we have set up the topics as getting more and more heavier and heavier into theory as we go. From like dynamic programming, you are writing every last step that you are for your algorithm. And divide and conquer, we give you a black box and we say, you know, you need to understand this because you need to modify it. In graphs, we say, here is the black box. You should understand how this black box works. But when you actually go and write a solution, you can just use the black box. You should just use the black box. You cannot modify any of the steps. But it doesn't mean like, you know, you shouldn't know how the black box works, right? Like that's the point of learning these black boxes. So yeah, you won't have to write all these steps out, but you should understand them.
Understood. Thank you.
Yep. Okay. And then so here are my two algorithms that you should understand. Know the different black box algorithms. Know the max flow is equal to min cut theorem. These are just, you know, things that you should check off as like you should understand this going into the exam. It gets a max flow for a flow network. The Ford-Fulkerson approach. It runs in all of MC, where M is the number of edges, and C is the number of your maximum capacity. Okay, assumes integer capacities. The way Ford-Fulkerson works and the way the pathfinding is undefined means that if the pathfinding algorithm is DFS and all your capacities are irrational numbers, and you don't actually have to know this. This is like some complicated proof that if you want to go look up, you can, or you can just trust me that I say it only works on integer capacities. It doesn't work on irrational numbers because the way it flips the capacities, it's going to go from saying there's a path to saying there's no path back and forth, and you end up increasing, decreasing your overall capacity, and you actually there's no way to end the algorithm in some cases. So the only thing you have to know about this is that if I ask you, can Ford-Fulkerson work on non-integer capacities, your answer is no. That's all you really need to gather from that. Or if I give you a problem that I specifically say does not have, you know, has irrational numbers as capacities, then you should not use Ford-Fulkerson. Pathfinding is not specified, but most assume that it means DFS. And sorry, my voice is getting tired. And then Scarps, on the other hand, is all of NM squared. It works with non-integer capacities. And the pathfinding specifically uses BFS. Neither is strictly faster. You have an M here, which is related, but this C, and when you factor this out, you have all of NM, oops, times O of M, right? And here you have O of M times O of C. Unless you have specific details about what the input is, you do not know if N times M is larger or smaller than C. And therefore, if I ask you which of these algorithms is faster, it would be undetermined. I might be able to ask you which of these algorithms is faster under specific circumstances when you know how N and M relates to C. But in a general sense, you can't tell me which algorithm is faster. Okay. Yeah. Ravi?
Thanks, Joves. I just want to follow up on what you just said about which algorithm works faster. What I was thinking, let's assume that we have a certain value for n and 1 for m. And let's just say that like we'll keep them the same for say the same max flow diagram. Are you getting what I'm saying?
I think you should, if you finish the question, I might be able to figure out what you're asking.
Yeah. Well, let's just assume everything is kept constant. Now, let's just say we want to vary the value of C. So if I was thinking that like in such circumstances, if we have a very, very high C, like say like 100 or 10,000 or something similar, then maybe the Edmonds-Karp algorithm could work a lot faster than Ford-Fulkerson. This is just a theory I'm bringing up, but does it make sense or not?
without knowing what N and M is, no matter how big C is, I can't tell you the relationship. Like N and M could be just as big as C or even bigger, and I would not be able to say that Ford Ferguson is strictly faster. Now, if you tell me N and M are 10 each and C is a billion, then yes, I can tell you that M Carps is faster in that specific instance. But without knowing all the numbers, I cannot tell you which one is faster, and you shouldn't be able to either.
But I understand that. That's what I was going to say. I was going to say, like, assume N and M are just small numbers, like say 10 or something similar, and C is a very big number. That's what I mean.
Yeah, I mean, at that point, it's just math. Like, you just multiply out the math and figure out which number is bigger, and that one will be slow.
But obviously, since we don't know N, M, or C, we can't tell which one works faster. Sometimes in some circumstances, like Ford Ferguson works faster, or in other circumstances, maybe Edmund's car works faster. But otherwise, we don't know.
Yep.
All right, thanks.
Yep. Shanek?
Hey, sorry. Maybe this is so in knapsack problem, we had a similar case where the runtime had the capacity in the runtime, and there we said it's exponential in inputs. Is that true here, or it's not the case here?
Yep. We call the knapsack problem and the knapsack algorithm pseudo-polynomial. And we will cover pseudo-polynomial more directly in the next topic, but it is considered pseudo-polynomial runtime. Here, O of MC is also pseudo-polynomial because it is dependent on a non-input size. C can be some big number but represented by less bits. It could be some small number. It's the magnitude that we care about in this runtime. So in this case, it is pseudo-polynomial. Now, you can say that they're in different complexity classes. One of them, O of NM squared, is in the polynomial complexity class, and O of MC is in the pseudo-polynomial complexity class. That said, when comparing the two algorithms directly, because they're using different terms, you cannot explicitly say one algorithm is faster than the other. So it is a little bit, that's sort of like the difference between a complexity class versus a runtime comparison. You can say that one complexity class is higher than the other, but you can't say for all instances one runtime is bigger than the other.
Okay, understood. Thank you.
Yep. And I wouldn't say like you have to like really understand that too much now. That is a topic we will be covering soon after exam 2. But for now, if I ask you which one's faster, your answer should be depends, or I don't know because I don't have the information for it.
Okay, thank you. Understood.
Pierre?
Yeah. Hi. So one question about this. So in the context of the exam, if we don't know anything about C, does it make sense to go to pick anything else than Edmond's carp?
If you don't know anything about C, you don't know anything about N and M, you can just pick one and give it runtime.
Like you just said, Ford Ferguson is pseudo-polynomial, right? So one could argue that it scales exponentially on the input number of bits.
You can argue that it is a higher complexity class, but you would not be able to argue that one is faster than the other in terms of unknown relationships between N, M, and C. Right. So in that case, I mean, if you really want to pick Edmund's carp and just be like, yeah, I feel like Edmund's carp would be faster, you can. That's fine. I'm just saying, like, if you pick Ford Ferguson, we're not going to knock you down points for it because we're not going to say Ford Ferguson is faster than Edmund's carp or slower than Edmund's carp. We just aren't able to do that.
Okay, that makes sense. Yeah. So it's like the worst case scenario does not apply here because you don't know anything about the inputs. Is it like that?
Sorry, say that again.
So you always consider the worst case scenario, right? When picking up runtimes. So I don't understand the relationship between these, right? So here you're saying that you don't know about the input, so you cannot decide which one is faster. How? Well,
So
maybe I
think,
miss.
okay. Okay.
I'm confused.
So I think students get confused between the different terms of worst case runtime, tightest bounds, and what we are after. I think Asia is working on a post to sort of clarify that a little bit. When we think about a worst case runtime, we think about it isolated to an input. Given an input of size n and an input of size, an m, what is your runtime of your algorithm such that no shortcut, no short circuiting happens? You run through all of the inputs, all of n and all of m. What is your runtime in relationship to n, m? A worst case runtime is not to say, how can I set up n and m such that your runtime is at the worst is the worst possible answer? What would C have to be for all of MC to be really, really bad? You're just saying, given some input of size m with an overall capacity of some C, what is the runtime if no short circuit or no lucky finds of your binary search happens? What is the runtime of your algorithm if it runs fully to completion? That is the runtime we care about. Okay, because yeah, there can be some gigantic C that happens that makes 4-focus-N really, really slow. There could also be some gigantic N or M that makes Edmonds Carp very, very slow. And without knowing any relationship between the C and N and M, I can't say which algorithm will be faster or slower.
Okay, that makes sense. Thank you.
Yep. Okay. So strategies to consider when using one of these algorithms is that you can turn a graph problem into a float network. So you can assign flow to a graph in order to turn it into a float network. A very good example of that is the bipartite problem, where you assign each edge a capacity of 1 in order to limit how many can go in and out of a node. So that's one strategy. Turn it into a flow network, even if you don't have initial capacities. You can update the capacities to fit the problem. So like, if you wanted to double the flow, maybe you double the capacity of all your edges, or maybe you shrink the capacity of all your edges. Various approaches to that. You can add nodes or edges to divert or add flow. So if you have to make very specific decisions between certain nodes, you might be able to add an edge or remove an edge or add a node in between them. So adding more nodes and edges to further restrict or unrestrict the flow network is a strategy. You can add more capacity. S can always be given more capacity because S has infinite capacity. So if you want to add an additional path from, say, A to, let's say you have like, S to A to B to T, right? And you're like, oh, I want to add an additional capacity from S to B, right? This can add a number. You can add a number here without worrying about S. S has infinite capacity coming into it. So S never has to worry about, oh, I run out of water to send over this new capacity. Okay, S is infinite. T is also, the incoming capacity is also considered infinite. You can also add more constraints. You can say, not only is my flow upper bounded by the capacity, it's also lower bounded by some demand number. I believe one of the lecture problems talks about demand. You can also, if you're trying to figure out what if you can do more to add more flow, you can first find a max flow, then create a residual network, and then work with it. You can work with that residual network to get more information about adding some capacity to one of the edges, either by figuring where out DFS or BFS ends. your BFS might not be able to find a path from S to T, but it can find a path from S to B, right? And so then maybe that's all I need to add more capacity is right here to increase my my flow. So that's one consideration. So that's it. That's all I have for focus in the image card. I want to give about a 3-minute break, and then we'll come back and try to go over the practice problems. I know this session is taking a while, but hopefully we can finish up the practice problems, and you'll be on your way. All right, 3-minute break, everybody. Thank you. Give everybody about a minute to get back. When you guys do this week's programming homework, let me know which one you enjoyed more. Curious. I designed both of them. I think most of the programming problems, I think every programming problem you guys have done this semester was designed by me. They're fun for me to do, and I have to solve them in order to for us to grade them. So I like to put the names of the other head TAs into the problems. I think it's fun. The coffee problem was actually based on a exam problem I wrote. So Sam mentioned the flow network has integer capacities. We should emit coupling set for focusing just to be safe. Sure. Yeah. If you don't know about whether the capacities are integers or not, you should use MX carp. Yeah. All right. Let's start doing some practice problems. All right. As always, I will sort of go through my thought process, and then I will paste the model solutions that you all should have already, and kind of go over in detail the different parts of it and why any parts are particularly important for a full solution. All right, so the question is, you are given a strongly connected graph, okay? So what does a strongly connected graph tell us? Well, even before it says strongly connected directed graph, if it's strongly connected, we know that it is a directed graph. That is what The only thing about a graph that would make it strongly connected is if it was first directed. Okay. The other thing we know about it strongly connected is that there are no islands. Islands meaning a vertex that is unreachable from any other that is by itself. Now there are vertices that are unreachable from all other vertices. Be careful, because if that vertex is a source, it is unreachable from all other vertices. There are also vertices that do not reach any other vertices because they could be a sink. But a strongly connected graph means that all vertices either have a path coming into it or a path coming out of it. Okay. We're told it has positive edge weights. This is also a big clue. It's got edge weights. We're probably looking for some kind of pathing, a shortest path answer. And because we're told it's positive, we know that if we are looking for a shortest path, we want die stress. Without having negative edge weights, Bellman, Ford, and Ford Warshall are not necessary because the advantage of those two algorithms is because of their ability to work with negative edge weights. We don't have to worry about that. Therefore, die stress is our prime candidate. So the next question part is, along with a particular node V0. Okay, so we are given some V0 that we want to consider as special. Given the efficient algorithm for finding the shortest path between all pairs of nodes with one restriction that these paths must all pass through V0. Okay, so we have a bunch of vertices. And this is a really simplified problem. And we have some V0, right? And we want to know the shortest path between this vertex and this vertex, and then this vertex and this vertex, that vertex, right? We want all pairs. Okay. So what do we need from this? Well, the first part is that we need to know the shortest path to V0, right? Because we have to go through V0. Therefore, we should all have our path going to V0 in some way, and we're looking for the shortest path. So our initial leg of our path, or the initial part of our path, should get to V0 as quickly as possible, or V prime. I'm going to call it V0, right? Once we add V0, we want to be able to reach all other vertices in the shortest way, shortest path possible. And now we want to know the distance from V0 to all other vertices using the shortest path. Okay. Now, do we know that there's a path between every vertex to V0 and between V0 to all other vertices? We do, because we're told that this graph is strongly connected. And if it's strongly connected, that means that every single vertex has a path to every other vertex. So I must have a path from a vertex to V0, and I must have a path from V0 to another vertex. So how do we find this? How do we find the shortest paths to V0, and how do we find the shortest paths from V0 to all other vertices? Okay, so the first part is easy. I want to know what the shortest paths from V0 to all other vertices are. That's exactly what die stress is designed for. So die stress does just that, right? So we want to go from V0 to all V and V, okay? We just set S to V0, and we run die stress, and that works. Now, the second part is a little bit more difficult. We want to know all the shortest path from all other vertices to V0. You don't want to run die stress from every single vertex just to get the information for V0, because that's inefficient. I've already told you, do not run a black box algorithm from every single vertex. Bad idea. I also told you when we covered die stress a while back that one of the strategies is to reverse the graph and see if you can get information that way. Now, it turns out that for shortest paths, V to V0 for all V, right? That distance is the same as V0 to all V. So if we reverse the graph and we run Dijkstra's from V0 and we get the shortest path from V0 to all other vertices, those same distances are the same as from V to V0 in the original graph. Okay. And that is what our algorithm will do. Let me just copy and paste the original one. What does our model say? We run Dijkstra's from V0 to get all distance from V0 to all vertices in V. Done. Reverse the graph and run Dijkstra's again from V0. The output corresponds to the distances of the shortest path from all other vertices to V0 in the original graph. Good. For any pair of vertices U, W in V, the shortest distance from U to W using a path from V0 will be the sum of the two distances, which is U to V0 in the reverse graph and V0 to W in the original graph. Any single path, which is U to V0 to W, can be recovered using the previous arrays, which result with from each run of Dijkstra's. Okay. Well, the problem asks for all pairs shortest path. Typically, problems in this course would request a structure or function from which those paths can be derived, or else simply calculate the distances above. We demonstrate this solution accordingly, showing how dist and prev can be used depending on scenario. See runtime for more. So we don't like the full context of this problem because it asks for a problem that's basically going to be O of n cubed. And that's not a great runtime because all your black boxes are under O of n cubed. So giving this problem as is, we result in students basically running any algorithm they want, and that wouldn't be great. So if we were to ask this question, we would ask correctly, get us the distances. We don't actually want the paths or something like that. Or we just say, give us a function or a data structure that would allow us to find it ourselves. So the justification of correctness algorithm works because our graph is strongly connected. So we mentioned any of the properties that our graph gives us because we can leverage it in our decision on which black box to use. So it's strongly connected, meaning that a path exists between every pair of vertices, right? We also know that Dijkstra's gives a starting, given the starting vertex and non-negative edge weights, we'll find the shortest path from the starting point to every other vertex. So we've explained why we want to use Dijkstra's, right? So why did you run the black box? Why did you reverse it? Well, reversing a graph, directed graph, essentially reverses the direction of the path between any pair of vertices. So the shortest path from U to W, which includes V0, is the combination of those shortest paths. Okay. We follow by the runtime analysis. Each run of Dijkstra is O of n plus n log n. That's a known runtime, which simplifies to O of n log n, since the graph is strongly connected. Because m dominates n here. But you don't have to do that. You don't have to write that. We have decided that that is not necessary. You can just leave it as Dijkstra's runtime. Building the reverse graph takes O of n plus m time. Obtaining the necessary structures, dist and prev, from which the shortest path can be obtained is O of m log n. So it's dominated by Dijkstra's. However, if we are talking about calculating the pairwise distance or reconstructing the graph, it takes O of n squared to iterate through all the pairs, and it takes O of n to follow with the prev array. So it gives you O of n cubed over a runtime if we actually wanted to build every single path. Okay. Let's see hands. Let's go Equin.
Hi, I just have two things I want to clarify. So the first one is look at the justification of correctness, the last sentence. Well, it's also mentioned in the algorithm part. You see in the last sentence, you said the shortest path from U to W, which includes V0, is the combination of the shortest path from U to V0 in the reversed graph That's where I'm not sure about, because the path from U to V0 in the reversed graph, isn't that the path from V0 to U in the original graph?
Yeah, I think it could be better worded. I think that's a good point. So
Okay, so it's not okay. So okay, yeah. Okay, in the reverse. Okay, cool. Thank you. And second one is, yeah, the note already mentioned, building that pair path takes O(n) square. So in exam, for example, if we're given a question of this, should the runtime be should the runtime analysis be stopped at O(m) log n? Or we should also include the O(n) square time for building that table for n pair,
we
n
would
to n
not,
pairs.
yeah, we would not give this problem in this way. On the exam, we would be very clear about wanting the runtime to be upper bounded by the black box that you choose to use. So this problem would not be given this way. If this problem was given it the way, let's say TAs and Dr. Britt had a lapse in judgment, we just like, hey, yeah, answer this question. If you wrote out the full runtime analysis, we would give you points for just understanding the runtime. We would be okay with that full explanation.
Okay.
Yep.
All right. Thank you.
Yep. Ravi?
Hello, Joves. I just need to understand the runtime analysis. When I did 4.14, I took into account the runtime for calculating the distances for as we were going through each edge. So I understood that for iterating through all pairs, since the problem already asked for all pairs, I understood that the runtime was O of n squared, and I factored that into my runtime. So which meant that I had a runtime of say O of n plus m log n due to using Dijkstra's algorithm plus n squared. I thought that didn't make any sense. But I'm trying to understand. When the graph is strongly connected, which means that does that mean that there are more edges than the vertices? Because like a strongly connected graph means that for each path from U to V vertices, there is always a path from V to U. So that's what I came to understand, that like there are more edges than vertices. Am I making sense?
If a graph is coded out to be strongly connected, or if a undirected graph is coded out to be connected, that means the number of edges is greater than or equal to n minus 1. And at that point, you can simplify that to be m is greater than or equal to n, which means that the number of edges is going to dominate the number of vertices.
Oh, so it's not necessarily a matter of domination. It's because in a strongly connected graph, we have m is equal to m minus 1, which just means m minus 1 be close to n itself, which is why you say simplify that, right?
Yeah, so it just means that one term dominates the other, and you can drop the other term when they're being considered together.
Oh, okay. And then my second question was, given that this kind of runtime amounts to O of m log of n, and would that mean like the overall runtime would mean that it's ultimately O of m log n? Because I was seeing the result because and I was trying to wrap it around my head, my mind.
So yeah, I don't quite understand the question. So the runtime is O of m log n for just constructing the data structure, not following through with it.
No, I mean for the overall algorithm. I was trying to get that around my head.
Overall runtime of the algorithm, we wouldn't get the problem in this format because it is kind of ambiguous, but like we would have accepted if someone gave this problem, the grading team would likely be directed to say all m log n is fine as long as they say that constructing the path would take longer. All n cubed would be fine as long as they said finding the data structure for that path is open login. Like we would be okay with either as your final runtime, as long as which is why we don't ever ask for a single runtime. We ask for an analysis. So as long as your analysis is complete, the final runtime is not the interesting part to us. Is understanding each part of that analysis.
Okay, but ultimately the final runtime for overall is M login in this kind of problem.
Like I said, like it just really, I mean, I think I don't want to give a definitive answer because this question was ambiguous to start, and so the final runtime is kind of ambiguous. We would accept either as long as the analysis is there. I think that's as complete an answer as you're going to get from me.
Okay, yeah. Also, O of M login is one acceptable answer then.
Provided that the entire analysis was there.
Yeah, of course. Thanks.
Yep. Okay. Any other questions about this problem? Cool. Next problem is 5.1 and 5.12. I actually don't know what this problem is. I mean, let me just check my own answers. Hmm. 5.1, 5.12. Okay, what is the cost of its minimum spanning tree? All right, what do you guys want to do? Do you want me to do it with prims, or do you want me to do it with crisscross? We can do either. Crisscross, all right. Crisscross, okay. So we could sort it, the edges, but we're just gonna pretend we sorted it, and we're gonna work through it by edgeways. I don't feel like actually writing it down. We can visually see. Okay, so if we have to pick from the lowest edges, we have 2 1s that we can pick from. So let's just pick one first. This is going to be our first edge. Our next edge is going to be this one. Okay. Now we are done with our 1 edges. We want to pick the 2 edges. So I see 2 of them. I could choose BF or I could choose EB. It doesn't really matter. So let's just go with this one for now. Okay. Now I continue down my sorted edges. My next one is BF. But because if I choose to include this edge, right, I will have created a cycle. They will have the same parent node in my union find. So I am going to mark it as considered but not used. I'm going to do that with this red right here. Okay. So the green is what my MSTs are, but I will mark edges as I go through them. Okay. Now we look at the 3 edges. I feel like going through this one first. Again, doesn't matter. Crisscross will work with either, and that's what's great about it. So that's my 3 edge. This is my other 3 edge. So I'll choose this one. Now we have to choose all 4. There's only 1. Yay. Now we have 5s. So if we choose this edge, that creates a cycle. So that's not okay. If we choose this edge, and now remember, when you choose an edge, right? It's not whether it forms a cycle with all the edges you've considered. It's whether it forms a cycle with all the edges you have in your MST. So when I look at this 5 right here, I look at it alongside my current MST, the current edges that I've chosen. I don't care about these 2. I'm not comparing this 5 to whether it causes a cycle with these other edges I've considered. They're not in my MST, so they're not going to be available to me for consideration. However, this 5 does create a cycle with this 4 and this 3, so that's why it's not considered, not because of these other 2 edges that I never considered. So once I go through that, my next 5 is this one. That does not cause a cycle. That's good. Now I go to my 6s. This would create a cycle, so that's no good. This would create a cycle, right? So that's no good. And then finally, the 7 would also create a cycle, so that's no good. So my final MST, and this is one of some, possibly more than one MST. Let me do this. We are going to say MST is the remaining edges. All right. So 1, have I connected my entire graph using my MST? Looks like it. 2, do I have any cycles? I do not. And 3, is it minimal? I assume yes, because I ran through Kruskal's algorithm by hand. How many edges do I have? Well, I have 8 vertices, so I would expect 7 edges, right? So let's count them. 1, 2, 3, 4, 5, 6, 7. 7 edges. Done. So actually, once I got to 7 edges, I actually did not have to consider any of the 6s or the 7s. I could have just stopped, right? That's would have been shortcutting it, but I wanted to follow through the rest of the algorithm. All right, so what is the cost? Cost is just the addition of all of them. So I have 1, 2, 3, 4, 5, 6, 7, 10, 19. Oops, use a better color. Okay, so that's part A. How many minimal spanning trees does it have? Ooh. Finding all the minimum spanning trees is not easy. It is considered and be hard. But because it's a simple graph, we probably could figure it out, right? So let's take a look. So we need all the 1s. Okay. We need all the 3s. So the only thing I can decide here is this 2. I could potentially change this 2 to this 2 instead. So that gives me at least 2, right? So right now I have 2 MSTs, okay? Now, I use a 5, so I have to consider what could I have used in the other 5s? Could I have used this 5? No, because I need this 3, I need this 4, and this 5 would have created a cycle. So this 5 could never have been chosen. The other thing is I could use the cycle property. Check that out. 3, 4, and 5 makes a cycle. The heaviest edge of a cycle can never be part of an MST. So this 5 is not possible to be part of an MST. Neither is this 7. Neither is this 6. This 6 is part of a cycle, so that can't be used. Okay. So the only other question I have is this 5. Can this 5 have been part of an MST? It turns out it doesn't, because I eliminated this 5 using 3, 4, and 5. I eliminated this 5 using a different cycle. So 2, 3, 4, 5. That is a cycle right there, right? Between these 4 vertices. And 5 is the heaviest edge in that cycle. So this could never be part of MST. So having eliminated all the vertices, all the edges I didn't choose, my only other choice was this 2. This 2 is not the unique heaviest edge in any cycle, right? In this cycle of 1, 2, 2, it is not the unique heaviest edge. In this cycle of 1, 2, and what was it, 6, it was not the unique heaviest edge. And then you kind of look at it, and all these other edges are larger, so it was not the heaviest edge in any cycle. So because of that, it could have been in part of some MST, and therefore it could have been a choice. And the only other choice was this one, so there should have been 2. I'm gonna guess 2 here. Okay, suppose Kruskal's algorithm is run on this graph. In what order are the edges added to the MST? For each edge in this sequence, give a cut that justifies its addition. I'm not going to do that. I'm just going to show you the solution to that, because that will take me a while, and I don't want to do it. But I will talk about it a little bit. All right, so first solution is 19. We came up with that. There are 2 possible MSTs. Good. So what order are the edges added to the MST? Okay. And then where are the cuts, right? So the cut is what cut am I using on one side versus the other subset that I'm saying this is a cut between. So for example, I want to say I want to include this edge as my first edge in MST. Well, if I say my cut is between A and the rest of my graph, that's the cut I'm using to determine that, okay? And then once I have that, I'm saying, okay, well, EF is my next edge I want to consider, and it's saying, well, my cut is AE versus the rest, okay? And the this actually isn't like so the way Crystal's works is that we're showing how we're building this this out, but it actually doesn't have to be like this cut doesn't have to be AE. I can justify well, no, I want this one to be a unique lattice edge. Let me see. So notice how like it says A and the rest of this. I can actually also say, well, it's a lattice edge across this cut, and that just works as well. There's a lot of cuts that can justify AE being added as the one of the lightest edges for your Crystal's. So that's this can be this section right here can be written in a whole lot of different ways. So just be aware of that. All right, any questions about 5.1? People want to see Prem's algorithm instead. What's 5.2 asking? Oh, 5.2 tells me to run prims, so we'll do prims on 5.2, and that should be good. Okay. Question, Matthew?
Yeah, suppose DH was not a high weight. Suppose it was 1. What would your cut have been there? So you're basically building your cuts on the left side, and then all of a sudden you're building a cut on the right side.
Yep, because this happens to go from left to right. It looks like that, but when you actually run Crystal's, it's going from the lightest edge to the heaviest edge. The edges are sorted, and then it goes through. It can jump all over the place. I could, when I do the ones, I would do AE and then EF and then do DH would be my next edge after that.
Got it.
And you should have seen that earlier in my in the lectures when I started in the office hours when I built my MST using Crystal's. I jumped from place to place because I was just going by lightest edge to heaviest edge.
Yep, cool.
Yep. Okay. All right, let's do 5.2. All right, 5.2 says run Prim's algorithm whenever there's a choice of nodes. Always use alphabetic ordering, starting from a dry table showing the intermediate values, the cost graph. I'll probably just run through Prims to show you what that looks like, but then I'll paste the table because I think it's probably easier to do. Okay, so we're going to start with A, right? Because we are told to start with A. Okay, now we look at A and we look at all the vertices that our initial vertex subset has, all the edges coming out of it, and we choose the lightest edge. Okay, which is this one. Okay, so now B is included. Okay, now all the vertices attached to both A and B, we are going to pick the lightest edge. I see 4, 8, 6, 6, 2. So 2 is the lightest. So we're going to take C. Okay. Next, I am going to look at all the edges that A, B, and C are attached to. Oh, yeah, all the edges, and I'm taking the lightest one. I want to say 2 is the next lightest, so we're going to take this one. Okay. And then from G, I have all these 1 edges. So I'm going to take the alphabetically first, which I believe is D. Yes. Okay. Next, I am going to consider go back to G because this is a 3 and this is a 4, so those aren't going to be better than my 1s. So I want to say F, right? And then this one right here, H. And then finally, I only have one left, which is E, and the lightest edge attached to E is 4. So that would be my Prim's algorithm. So it goes A, B, C, G, D, F, H, E. Did I get that right? A, B, C, G, D, F, H, E. Okay, so it's the right order. The edge that gets included, right? So this is the edge that gets used. Accumulation of my weight. So when I first start with nothing, I have 0 weight. And then when I add A, that's also still 0 weight because I added a vertex, but I didn't add an edge. Then when I added AB, I got 1. Then when I added BC, I add 2 to it, so it's 3. And then when I add CG to it, that's 2. That makes it 5, so forth until 12. And then show the intermediate values of the cost array. Okay, so that's that one. So that's Prim's. Any question about the Prim's approach to this? Eduardo?
Yes, so quick question. On this particular example, we're told to start from node A and follow an alphabetical order. What if that wouldn't be the case? Do we start at a, arbitrary vertex? What's the... Okay.
Do you want to see what that looks like? Do we care? Do we want?
I don't care necessarily, just wanted to know. Okay, yeah.
Yep. Okay.
Okay.
Yeah. So if you start with the arbitrary vertex, you wouldn't necessarily get the exact same MST, but it would be a valid MST doing it that way. Okay. So the second one is run Kruskal's algorithm on the same graph. Show how the disjoint sets data structure looks at every intermediate stage, including the structure of the director trees, assuming path compression is used. Okay. We'll show that in a bit, but I'm just going to manually run through Kruskal. So I sort all my edges, but I'm just going to run through them in my mind. Okay. I will. Doesn't really matter which one I pick. So I want to pick all my 1s first, right? Because those are all sorted to the beginning. So this one is a valid edge. This one is a valid edge. This one is a valid edge. And this one's a valid edge. Okay. So after I run through all my 1s, I have 2 set of parents. Okay. So at this point, I have 2 parents, and I am just going to start picking higher weighted edges from the 1. So the next one is 2. I can pick this one, or I can pick this one. I'm just going to pick one though. Pick this one. Okay. So that edge gets used. My next 2, this one. Okay. It's also valid. Okay. So now I have most of that. From there, I'm going to consider 3s. I considered this one, which would connect C and D, but they are already connected and they are already in the same disjoint set. I just realized that the class teaches this data structure as union find and then calls it disjoint sets here. They are the same data structure. I don't know if the book ever tells you that they're the same data structure. Tim, are you here? Have you ever noticed that? Does the textbook mention that they're the same thing? That's interesting. I should check. Okay. So we don't want to use 3 because it would put them into the same disjoint set. So that's no good. Next one we consider is 4. This is the one we want, but let's just say for the sake of making it more interesting, we consider this one, but it's not okay because these are already connected. So the next one we can do is this 4, and so this is done. And this actually completes our MST total. But if we let our MST algorithm continue, then this one is eliminated in that order. Okay, so that is our MST. And then let me paste what that table looks like based on the model solution. Here we go. I want to put it on here so it's visible. All right, sorry, I'm going to cover up from this part. All right. So these are the starting pi. I call it parent. Apparently, you can call it pi. So for A, B, C, D, E, F, G, H, each of them are the same, their own parents. And then when I combine, when I decide to connect A and B, I choose one arbitrarily at this point to say, okay, B is going to represent both of them. Okay. Then the next one I'm going to pick is F and G, and I'm going to say, okay, F and G is going to be represented by G. You pick one arbitrarily. And then DG, which is right here, we are going to do DG. We're going to represent it by G, because at this point, you have a ranking of different things. So you want to take the higher rank of the parent because there's more pieces under it already. So because G is already used, G has a higher rank than D would. So when we put the two together, we're going to say, okay, D, you are going under G. And so we assign this to G. Now, when we do GH, similarly, G already has a higher ranking. H just got added, so G will be added. H will be added under the G umbrella. Then CG, again, same thing. G already has a bunch of followers. We're going to put C under G, so this becomes G. And then B and C, because C is already G, when B gets added, we are going to say, you know what, B, you are now under the umbrella of G, and assuming path compression is used. So this should have been updated to G at this point. So that's wrong. So we will fix that on our end. And the reason because of that is basically saying, okay, when something gets added underneath something, we are going to path compress. We're going to make sure that they're all go along with it. So we are going to path compress this into G. And so then when we add E, we already have G as a much higher ranking. And so E becomes G because, if you don't path compress this this A into G, then this would still be a B, and this would be put under B, and that's not the greatest. So when you do path compression, this has to be updated along with all of B and its children gets updated along with it. Okay. All right. Any questions about 5.2? Robbie?
Hello, Joves. Can you hear me?
Yes.
Thank you, Joves. I need to understand this disjoint jets data structure, because I'm not understanding this data structure or this parent pointer pi that you meant that is mentioned in the solution. Wait, can you explain that? Because I'm concerned that this could appear in either the content quiz or the second exam or both.
I mean, I would go look up a YouTube video on how to do how disjoint sets work. But very high level, what it's saying is that if I have a bunch of items, okay, and I go, okay, well, if I want to put these two together, I circled them and I assigned one as my representative. This B is representative of this this subset. And then if I want to grab this one, I'll say, okay, you're the representative, and this one I say, okay, you are, and then this one I say you are, right? So the initial part of it is kind of arbitrary. Now, when I want to union these two, I go, okay, well, I have two representatives as well. Pick one of you to be the representatives, right? So now my next circle is this one, and I go, okay, I am going to, make everything represented by B again. Okay. Now I could either union these two and again do the same thing, or I could say, okay, well, I'm going to union CD with this one. As a representative gets more and more children underneath it, its rank goes up because there is less to update when that happens. If you just arbitrarily pick one of these as a parent, and I pick this one, now I have to update the children. I mean the representative of 4 elements. Whereas if I say, okay, this one has more elements in it, therefore I choose this same thing to be the representative. When I merge CD into it, I only have to update 2 elements. So let's do that. Let's circle this in here, and okay, and I say B is a representative. Now the same thing happens with G and H, and I do the same thing. Now, what can happen is that because there's an edge from, let's say, D and E, is an edge from D to E? No, D and C. Okay. Well, this isn't representative descript, but anyways, if I did not know that, if I wanted to see if I can merge C and E, I go to C and I say, what is your representative? Who represents the group that you are in? Well, it's B. And I say to E, well, who represents the group you're in? Well, it's B. Well, if we're both represented by the same element, we are already in the same group, so there's no need to merge us. Okay? And now when I go merge G in this group into this one, similar thing happens. I take this, I stop that from being the representative because it's of a lower rank, and then now they're all together. Now, anytime I try to continuously merge any of these elements into the same group as the other element, because they're all represented by the same element B, I never try to merge them in. And the whole point of this joint set is to combine sets in as you work through them, and you say, oh, I've handled this set. I want to put it into my into a subset of I want to combine it with something else. You don't redo the work over and over again, because otherwise, if we don't have this disjoint set, every time I consider edges, I have to check all of the other vertices to say what edges, what vertices are E connected to, and what vertices are F connected to, and is there an intercept such that I know they're already connected. That's inefficient. That's why you have a disjoint set to set up this representation of all the other vertices in the group. And so then the check to see if they're represented in this by the same parent, or asking the question, are you in the same connected component, or are you already part of, are you already connected? Is it all one operation as opposed to all n? Okay, and that's what disjoint sets are used for.
Okay, thanks. I'll look into this, Joves, as you said.
Trying to remember what my interview question was that made use of disjoint sets. I'm trying to. Can't remember what my question was, but I made use of this on one of my algorithm, my interview questions. All right.
Thanks, Joves. I'll look into this as you said.
Yep. Okay. 5.9. Ooh, a whole lot of these. Okay, cool. Goes through A, B, and C, and D. Let's see if we can answer A, B, and C, and D. All right, the following statements may or may not be correct. In each case, either prove it if it's correct or give a counterexample if it isn't. Always assume the graph GVE is undirected. Do not assume that edge weights are distinct unless it is specifically stated. Okay. If graph G has more than, sorry. If graph G has more than V magnitude V minus 1 edges and there is a unique heaviest edge, then this edge cannot be part of the minimum spinning tree. True or false?
Should be
Dude,
true
someone.
because tree should have n-1 edges and only n-1 edges.
Right. But it's saying that if you were given a graph that had more than n-1 edges and you had to build a MST out of it, can the unique heaviest edge be part of the MST?
The unique heaviest? No. I think that was one of the properties we discussed earlier. Is that I think it's the I forgot which property it was.
So you're thinking of the cycle property, right? And
Yes.
the cycle property states the unique heaviest edge of a cycle cannot be part of MST. The reason why it's a cycle property is because it's very much specific to the heaviest edge in a cycle. But a heaviest edge may not be part of a cycle. And if that's the case, it actually has to be part of the MST. All edges that's not part of a cycle, unique or not, has to be part of an MST because there's no other way to get to all the vertices unless you take those unique paths. So consider the idea that if I have a very, very simple example. This is a unique heaviest edge, right? And I go C, D, what's that? 1, 2, 3, 4 edges. We can add a few more just to be safe. 1, 2, 3, 4, 5, 6 edges. 1, 2, 3, 4, 5, 5 vertices, right? So this is greater than -1, and these can all be 1s. That's fine. But because the only way for A to be attached to the MST that results from this edge has to be included. And if this is a unique heaviest edge, regardless, it still has to be included. So this answer is actually false.
So the reason it's false is because we're specifying it's a unique edge?
No, the reason it's false is because we do not say that the unique heaviest edge is part of a cycle. If the unique heaviest edge of a cycle must not be, cannot be in any MST, it's actually also true in the other direction. A heaviest edge, the unique heaviest edge that's not part of a cycle also has to be in MST. Any edge that is not part of a cycle has to be in MST because that's the only way to keep those vertices connected.
So
Right,
this is because the converse of the cycle property. If it's part of the cycle, it should not be included. But if it's not part of the cycle, it should. Sorry, reverse. If it's part of a cycle, it should not be included. If it's not part of the cycle, it should be included.
I'm not sure if that's like the exact converse, but the intuition is just if you don't have a cycle, right? Remember how I said a unique path between any two vertices must be part of the MST because there's no cycles, so that's the only way to get to connect those vertices. And so if A, B has a unique path, it doesn't really matter what that edge is, whether it's a light one, a heavy one, the heaviest one, it has to be included in our MST.
So again, just because I want to make sure I understand, it's due to the fact that it's a unique edge that is not part of the cycle.
It has nothing to do with the uniqueness. It has nothing to do with the heaviest. I am trying to prove that it's false by contradiction and by just saying that we know that any edge that is not a cycle edge has to be in an MST. Whatever weight that edge is, it'll be in an MST.
Understood. Okay.
Yeah.
I
And
get
if it's the heaviest, it's allowed to be in an MST, and so that one's false.
So this is just
Okay.
by contradiction. Gotcha. Okay. Thank you.
Yes. Yep. Yep. All right. Part B. If G has a cycle with a unique heaviest edge E, then E cannot be part of the MST. True or false?
This should be true because we just stated the cycle property.
Yep. So this is true. Cycle. Okay. Oh. God, my handwriting is so ugly. I wish that's something I could like just fix to have better handwriting. All right, part C. Let E be any edge of minimum weight in G, then E must be part of some MST. So carefully, let E be any edge of minimum weight in G,
False.
then E must be part of some MST. False.
I mean, if you look at the graph on the right and you assume that you did A, B, B, C, C, E, and E, D, then C, D, while it is a minimum weight, cannot be because it will create a cycle.
Okay. So these questions are tricky, and MST questions tend to be tricky because it's always messy with always and some and not all. So the answer is true because it's saying must be part of some MST. It doesn't have to be part of every MST, nor does it have to be part of the MST that you're actually working on. It just has to be part of some MST. And because CD is is the lightest edge, I can create an MST with that edge somehow. So what happens is, remember, Kruskal's will start off by picking the lightest edge, but it's not deterministic of which one it picks. It very much could pick CD as the first edge to be part of its MST. So what happens if we do that? Once we have that established, we can build an MST around it. That is an MST. That is a 103 MST. Alternatively, any of the edges that have a 1 on it, I can start with that edge and build a valid MST. And so the statement that E must be part of some MST is true. Some MST will make use of that edge. Okay. So when you answer these multiple choice type questions on the exam, be very, very careful and be very, very particular on what some all means. Okay. Part D. If the lightest edge in the graph is unique, then it must be part of every MST. So there's a different way to a different question. Anybody want to take a shot?
Can I try?
Sure, absolutely.
So I'm thinking that for part D, it has to be true because let me come to that in a minute. It has to be a part of every MST because in every MST we always pick out the lightest. No, what do you say? The edges with the minimum weight before we proceed to the edges with the next minimum weight. That's how Kruskal's algorithm works. So I was thinking that for this, this is proof that the lightest edge in the graph has to be part of every MST. So that's why I'm thinking that not only I think this should be proof that it's true.
So it is true, and the way we prove it is we actually use the cut property on this. So the cut property tells us that the minimum edge across a cut must be in some MST. If the minimum edge across a cut happens to be unique, then no other edges can be picked because no other edges can be a lightest edge across a cut, and therefore because a MST is a collection of the lightest edges across every cut, the unique lightest edge can be the only edge chosen across one particular cut, and therefore that unique lightest edge has to be used in every single MST because that cut has to be accounted for in every MST.
Right, and cut property too, yeah.
Yeah, so because the cut property, it is true. Okay. It's 5:42. I can cover the rest of this problem if you guys want to hear the rest of the solutions. I know that we only cover A through D on the model solutions, but I can cover the rest. Yes, okay. Let me bring up my notes so I don't make mistakes. This is 5.9. I think this is the last problem we have today, so we can cover the rest. All right, so part E says, if E is part of some MST of G, then it must be the lightest edge across some cut of G. All right, so you want to take a shot of E? Okay, so it is true. It is true. It is because if we only pick edges that is the lightest edge across some cut, right? That's because of the cut property. Therefore, any edge in an MST is the lightest edge across some cut. Okay, so it is basically the repeat of D. It's just another way to state the cut property. Okay. F, if G has a cycle with a unique lightest edge, then E must be part of every MST. Unique lightest edge. This one's a tricky one. This one is sort of a combination of unique lightest edge and MSTs. Anybody have a guess at this one? F?
If it's a unique and it's the lightest,
yeah,
then
of a cycle
of a cycle.
Yeah.
Wait, hold on. It's the unique latest of a cycle, or it's the latest in the in G.
The unique on a cycle.
So it's not the latest in the whole graph.
Of just a cycle.
Oh, then sorry, never mind.
So this one is again a tricky one, and it's best illustrated if I draw a graph. So yeah, when in doubt, just try to draw a graph. So if I have this triangle right here, right, this is a cycle regardless of what this is, and I say, okay, 2, 2, 4. Okay, this 4 is unique, right? But we don't know if it's included there's no property or rule that says whether it's included or not. We have to figure it out. But this edge, any edge can be in 2 different cycles. Now, what happens if I make this cycle and I turn that 4 into the heaviest edge, unique heaviest edge of a different cycle, right? We don't have a property that says that, oh wait, so it's unique lightest. Sorry, I messed that up. Oh my God. Sorry about that. So I can just do this instead, and it would just work just right. So that's the unique lightest edge. And this is always also the unique heaviest edge. And the unique heaviest edge of a cycle cannot be used in an MST. And therefore, if it's both the unique lightest edge of a cycle, but also the unique heaviest edge of a different cycle, it cannot be part of MST. Right? And so in that case, F is false. And the MST for this would actually be, we start off with the 1s, right? And then what happens to this 4? This is the next one we want to choose, but we can't. We have to choose this instead, right? And now MST is either this edge or the other edge, and that 4 cannot be included. Okay, and this is a application of the cycle property as a contradiction. We are on G. The shortest path tree computed by Dijkstra's algorithm is necessarily an MST. Is that true or false? I see students are hesitant to answer it after being tricked. This is how you lose faith. This is why you don't trust things. Okay. The answer is false. That's correct. So the shortest path tree computed by Dijkstra's is not part, doesn't have to be part of MST, because the shortest distance is computed over all the edges, but each of those individual edges may not be the lightest edge in a given context. So G is false, and the MST might include the lightest edge between it. So like, what's a good example here? Let's try this. Let's do.
Can a path have dead ends?
Did a path have dead ends? What do you mean?
Like in an MST, you can have, for example, paths that kind of just cut off at the end. Like if we look at one of the MSTs you shared with us prior, so like for example this one here, there are some like dead ends where, for example, you can get to A, B, C, G, F, but you can't get to F directly from E because there's like a dead end there. Same thing with like D. So can an MST be considered a path? It's a stupid question. I'm just curious.
I mean, at some point, all MSTs have leaves, right? And leaves, once you get to it, you wouldn't, unless you double back, you wouldn't have anywhere to go afterwards. All MSTs have leaves because they're trees and they have leaves. Trying to come up with numbers here that would make this work. I kind of want to go with, what's a good number to add here? So I want this to be my shortest path. So let's say
Ravi says he has a counterexample in the chat if you want to use that one.
sure, that would be helpful. I'm so bad at these things. Let's see.
ABC cycle, where
ABC
Yeah, I just
cycle.
specified that. So. I mean, if it's wrong, please forgive me.
AB is 100. Okay. BC is 2. Yeah, that works. That's a good one. Yeah. So the shortest path here would be A to C is 101, right? But that's not part of my MST. My MST is going to be this 100 and this 2, even though my shortest path from A to C would be 102. Good job. That works.
Thanks.
Thank you. Appreciate that. Yep. All right. So that's a counterexample. Part H, the shortest path between two nodes is necessarily part of some MST. I think that's the same problem, right? That's the exact same question. Is that even a different question? Yeah, I don't think that's a different question. I just think it's just asked in a different way. Prim's algorithm works correctly when there are negative edges. That should be true. We've already talked about this. MSTs are making greedy decisions locally, and it doesn't care about any other additional information. And so if it's a negative edge, it'll just choose it if it's minimal, and that's fine. Part J, for any R greater, actually, let me write down the answers here in case anybody wanted to actually. License graphs unique must be part of MST. We said this is true. If he's part of some MST, it must be a license across some cut. That's true. Cycle has unique license. We said that's false. Dijkstra is false. This one's false. This one's true. Okay. Final question. For any r greater than 0, define an r path to be a path whose edges all have weight less than r. If G contains an r path from node S to T, then every MST of G must also contain an r path from node S to T. I'll be saving those pictures, right? So if you start bragging about your so it just all have weight less than r. Okay, if G contains an r path from node S to T, then every MST of G must also contain r path from node S to T. Yeah, so that is true. Right. And the reason why this is true is basically saying that if I have a path from S to T where all my edges is under a certain r, some number, right? Then when I build the MST, I can only go lower than that r path, because if I didn't have an r path from S to T, so if my MST didn't have an r path from S to T, then there exists some edge within the r path that I know that goes from S to T that I can swap out the edges for that would make it into an r path, right? Think about it. If I know that there's a path from S to T with a bunch of small edges, the question is, can I get a MST from S to T that has a bunch of small edges? And we know those small edges exist because we know that our path exists. Therefore, the answer is true. Why would I pick an edge that is bigger than my R value if I know an edge exists that's under that R value? Okay, and so that is true. Okay, any questions about 5.9 before we call it a night? Eduardo?
This is not a question related to 5.9. Is it okay if I ask a question?
Yeah.
Okay. So you mentioned at the beginning of today's office hours, and thank you so much for putting this together, that you didn't do super well when you did this class. And then you mentioned that you studied a little harder for graphs and subsequently for NP problems. What approach did you take? I feel like there's an overwhelming type of amount of information that we can leverage, and I feel like one of my mistakes was maybe trying to take it all in, and then I got even more confused. So I'm curious of your approach or your suggested approach as we prepare for exam 2 and subsequently exam 3.
Yeah, that's a good question. I think the most important part is sitting down with yourself and being honest with what you thought you lacked going into the first exam. Any student that says, "Oh, I did everything perfectly, I studied perfectly, there's nothing wrong with me," is just not being honest with themselves, and they're not going to improve. And this is true about anything that you want to get good at in life. Like, it's not just this exam, right? Like, no matter what you want to get better at, there is always ways to get improved. All the best people in any given field can improve in some way. So I thought I did a really good job of setting up a study group. I had that going into exam 1. I did every single homework problem. I did every single practice problem, and I watched all the lectures once. And so I looked at it and I said, what did I do wrong on my exam? What can I improve on? Even if I thought, like, there's a 50-50 chance I could have done it correctly, what can I do to make that 75-25, 85-15, so that the next time that situation comes up, it wasn't going to be a problem. I think what it was for me, and I realized, was that I went into the problems thinking, oh, I can come up with a solution. And when I come up with a solution, I'm going to write it correctly. And what I failed to do was, after thinking I got the correct solution, not considering the mistake I was making, not considering that, oh, what I'm writing in my mind is the correct solution. I never even doubted that it was the correct solution. So I worked harder. I looked into more of the regrade threads, and I think that's why it's one of my high recommendations for students coming into the classes. I looked at what mistakes other students would make, and so I could recognize the pattern of making a mistake because I had that as a blind spot. Because I did so well on my homeworks that I did not make mistakes on them, I didn't know that I was making a mistake because I couldn't recognize it in my own on my own exam. And I think after I worked much harder on going over people's regrades and saying, oh, you made a mistake here. When it came time to the exam, even if I didn't make that mistake on the homework, as I was writing the exam, I go, oh no, that is a classic mistake when approaching this type of problem. I need to make sure that's not the mistake I'm making. So I think that was like a big jump in terms of my understanding of future topics. This can be very different from student to student, but I think it starts with a introspective of, a why of how you missed the points that you could have gotten, and trying to attack it and force that particular weakness to not be a big weakness going into the next exam. So that's what I would recommend all the students is sit down. That issue proactively going into the next exam.
Thank you.
Yep. Yeah. So Tim suggests that bandwidth from many more homework problems. Yeah. So now your homeworks aren't like weighted, and so some students might take it easy or say, oh yeah, I could probably get this wrong and it's okay because it's not worth anything, or yeah, I can skip this homework, it doesn't affect my grade. If you are skipping homework assignments, that is certainly going to impact your grade. The more practice you get, the better you can do. And talking with other students, finding out their perspective on it can only improve your own approaches to these problems. Ajmal?
Thanks, Joves, for the wise words. Just a question, like, do you have
They're only wise because I make mistakes. That's the only way to become wise, is to make the mistakes to tell other people to avoid them.
Appreciate it. Just wondering, do you have any go-to toy examples of graphs for solving these MSTs and just graphs in general? Because sometimes I'll come up with a graph and like, oh, this works, but then some counterexample comes out and like, oh shoot, that doesn't work. So do you have any go-tos?
I like a straight path. This is my thing for a lot of problems. Just a simple straight path, make sure my algorithm works on that. I like to do the triangle. And then if it's a undirected graph, you're done. Otherwise, I like the variations of, the triangle being a full cycle, or the triangle, doing that. Where like, there's a source and a sink in my little triangle. The other one I like is this one. That's just kind of like a multi-path little toy graph that I can do. So you can go, this way, you can go this way. So I think those are most of mine. There is complete graphs that you can use, but that's sort of like a later topic. For graphing problems, I feel like these three typically sets me up for success. Anything that's MST/Dijkstra's related, I will take this top graph and I will additionally add this path, making sure that this edge is less than these three summed up, but each of these edges are less than this edge, and that just catches any sort of like issues where you're trying to add additional weight or remove additional weight to try to shift your graph one way or other. I feel like this particular graph helps me catch any issues with that approach. And then come up with your own, share them with the class. It's always cool to be like, hey, I use this graph. all the time when I'm making problems. So when I write your programming homework problems, you will see some of these graphs show up because that's what I use for my toy example. So I kind of use them for base cases as well. You will particularly see this one right here as one of your toy examples, as one of your base cases, because I find that one to be a pretty good one.
Thank you.
Yep. Any other questions?
I had one other one about exams in general. Well, actually, for the next exam too. I was wondering if is it possible, would you guys consider releasing the multiple choice results for the next exam, given that it's in the middle of